Matt Kafker is one of our research affiliates in the program. He's been there almost since the first physics summer school started. And since then, he has been doing really interesting and exciting work in connecting aspects of the Wolfram model to statistical mechanical systems. It's going to be a great session. What he's going to talk is really exciting. So I feel free to engage and feel free to interact and stop anytime. In case there are questions, you can put them in the chat, or as Matt said, you can interrupt. If you don't see the screen, I can just kind of give you a notice or whatever you like.
I'm experiencing an embarrassing technical difficulty here. I have all of these notebooks open that I was comparing to, but I really don't want to present from them because they're old and terrible. So I want to make sure I'm showing you the right one.
Go ahead.
Okay, are people seeing a notebook here that has
yes, it's called Hard-Sphere Particle Simulations and the Wolfram Model.
Okay, people are seeing this. Great. Actually, you know what? Before I do this, I would love to know who I'm talking to. For those of you who are feeling courageous enough to speak up or like throw this in the chat, maybe. Here, I'm going to exit full screen for a second. I'm just curious, people, undergrads, grad students, PhDs in physics.
It's a mix. It's a mix.
Yeah. Okay. Okay. I'm not exactly sure what I'm going to do with that information, but I was just curious. First year physics master. Okay, right on. Okay, and if me drinking coffee is eking you out, then tell me and I'll mute myself when I take a sip of coffee. Okay, let's see here. I gotta make sure I can see people's faces, but also somehow have access to the chat. All right, cool. Well, it sounds like some of you guys are approximately sort of my level of education. This talk is entitled Hard Spheres, Particle Simulations, and the Wolfram Model. I'm Matt. So I'm in the Department of Physics at the University of Washington, and I'm a junior research affiliate on the physics project. I've been primarily working with Xerxes, but also with Christopher, whom I haven't seen around in over a year. So I don't know what he's up to these days, but I've been collaborating with him. So here's what this talk is not. I'm going to be talking about computational statistical physics, physics on graphs, machine learning in physics, and the Wolfram Physics Project. But I'm not going to be doing a comprehensive review of any of these things. I'm not qualified to do so. I'm basically just going to be talking about the things that I've been working on that are sort of the sort of direct downstream consequences of my initial summer school project, and also sort of the things that I've learned along the way. This is not paradigm smashing science. A lot of you are doing incredibly fancy fundamental physics. That's not what this is. This is a little bit more conservative, but that doesn't mean that it's not interesting or new. I think that it's both of those things, and we're going to sort of go all over the place here. So, and also this is not done, but yeah, very broadly speaking, physics simulations in the Wolfram language and connecting them to the Wolfram Physics Project through causal graphs. I couldn't resist this. So over the summer school, I don't know if any of you were here at the summer school, but Nassim Taleb gave a talk and I loved his books. They're hilarious and very sassy. And he has this trend that he does where he titles his chapters sort of these inscrutable things that make you want to sort of read on and figure out what on earth he's talking about. So here's my clickbaity list of inscrutable things that we're going to talk about. So we have microbes or molecules, microbes in the Milky Way, suds, orange peels in a 400-year-old mathematical conjecture, bird flocks as condensed matter, teacher laptop to be a theorist, you tell me how to coarse grain, a Rosetta Stone and a treasure map, and the physics fix. So that's not supposed to mean anything, and those are supposed to be sort of silly and intriguing, and if you think they're stupid, I probably agree with you, and we won't be referring back to that list, but I could not help myself. Okay, does anybody want to say anything before I get started? Because I'm going to jump right into some physics here. All right. Okay, so the starting point for basically this entire discussion is going to be this notion of a particle simulation. So I've got a bunch of particle simulation stuff here, and I'm going to tell you about it. So this is generally what we're up to, what I mean when I say particle simulation. These things have a lot of different names depending on whose papers you're reading. They're going to be called something or something else. But basically the idea is we just have a system of particles that are obeying Newton's laws of motion. So we have, we have F equals ma, and we have V equals dx dt. Pretty standard stuff. And we imagine that we have I particles. So these are going to be indexed by some index I. And we want to update the position and velocity in time. So we can just do a first order Taylor expansion and we end up with these equations, which many of you will probably have seen before. So the velocity at some later time is equal to the velocity at the current time, updated by the force times dt. I've absorbed the mass into the force term here. And the position is updated by the current position plus the velocity times dt. This should not be shocking to anybody. If I need to clarify, please let me know. But the idea is that we start with some initial conditions at t equals 0, and by iteratively applying these equations, we arrive at some different configuration at t equals capital T, whatever that may be. Any questions about this? This is high school calculus. The first part of this talk is basically all high school level stuff, which is pretty cool because it goes far beyond what you're taught in high school, but the technical level is pretty low. So this is forward Euler. In some meaningful sense, this is like a terrible integration technique, but we're going to get a very long way by using it. So that's where we're going to start. So this is interesting because we didn't need to say what the particles are, and we don't need to say what the force is. We can just sort of express this very generally in terms of general forces. So this is going to allow us to simulate a ton of things. I actually, last night while I was preparing the talk, I was curious what the sort of reasonable range of length scales. So you can use this to simulate atoms, molecules, cells, insects, fish, birds, planets, stars, and so on. And this is actually sort of relatively conservative. I think you can keep going on the upper end of this list. But if you wanted to use this to simulate sort of galaxy formation, maybe you have the size of the Milky Way compared to the size of a hydrogen atom. This is something like, I wouldn't take this number too seriously, but something like 31 orders of magnitude of length scales that can be reasonably discussed using this like first semester high school physics and putting it on a computer. So that's pretty cool. And I'm gonna just go into a couple of examples of this. Unless anybody has any questions before I move on. Okay. So let's actually look at a couple of these. So basically a really good first one to start with. The general theme of this section, by the way, I should say this before I move on. We're just going to be choosing a bunch of values of this force and more or less directly putting it into these equations and then visualizing the evolution here. Okay, so we'll start with this potential, although this is sort of misleading if or unnecessarily complicated, but just keeping things in the framework. Let's say we have no potential in the box and an infinite potential at the boundary and outside the box. So everything is just going to move around in a straight line and reflect when it hits the walls. And this is going to be geometric or ray optics. So if we evolve forward in time, all right, perhaps this is not surprising. Our light rays are going to bounce off the walls and do something like this. So really simple starting case, reflecting boundaries here. And, you know, if you wanted to add more detailed optics, you could do that with sort of if statements as well. But this is just a pretty good example of the first type of thing that we can do with this simulation technique. Okay, so again, jump in at any time if you want to have a discussion about any of this. I can try to go quickly over the parts that are straightforward. So this talk is nominally about hard spheres. I'm going to introduce them here and then depart for quite a while before I come back to them. But we're just going to introduce the model here. So this is a hard sphere system. This is the potential energy. So it's a pairwise potential. And it's 0 if the particles are sufficiently far apart from one another. And what that means is that if you imagine two circles, each of them has radius rad, as long as they're more than 2 radii away from one another, they're not touching and the potential is 0. but the potential will be infinity if they're less than 2 radii away from one another. And what that means is that they're going to move in straight lines until they come into contact with one another, in which case they're going to scatter elastically. So momentum and kinetic energy are going to be conserved in this collision. And this is interesting because they also have spatial extent. So if we take a look at this simulation on the left here, we're going to send them in at one another, and they have a non-zero sort of impact parameter, so they're off center from one another. And again, not exactly surprising physics here, but you'll see that they bounce off one another, and there's no momentum in the vertical direction before the collision, but the sort of spatial extent of the spheres means that there is momentum in the vertical direction after the collision. So this is like a billiard ball simulation. There's a lot of different names for this. Hard spheres is a particularly parsimonious name that appears to show up a lot in the literature. So that's how I'm going to talk about it. And obviously we're going to be concerned with not just things like this, but simulations that are sort of closer to the sort of interacting gas liquid type phase. So this is a sort of a semi-dense, what you would call a simple liquid, and we have periodic boundary conditions. So if the particles appear to be bouncing off of nothing on the tops and bottom, they're actually sort of colliding with one another on the edges. So the top is the same as the bottom, and the sides are the same as one another. So this is a great tool for doing computational physics. I didn't really know this. I sort of came across this information, but it immediately left my brain when I had encountered it in the past. These are one of the first physics simulations that people ever sort of took seriously and did. 1950s in Los Alamos was when people started researching these things, and they've been more or less continuously under investigation since then. So the fact that we have something new to say about these is kind of cool. And I hope that I will convince you over the course of this talk that we actually do have something quite new to say about them. Are there any questions about what's going on in the hard sphere case here? All right, by the way, I'm looking over here because that's where your faces are. The presentation is in front of me. So if I keep looking off to the right, that's what I'm up to. Okay, so these are some simulations. These are written in Wolfram language code. They run in higher dimensions, which is kind of cool. So here's a nice little dense sort of crystal-like thing where all of our hard spheres are bouncing around, and they have sort of like a little bit of order there. If you're curious what the code looks like to actually run one of these computations, I've written this function called many-body simulation. It's changed its name like 10 times, and it's going to change its name again. Now I want to call it particle simulation, and I'm sure next year I'm going to want to call it something else. But this is the type of code that I'm going to be running in this notebook, and sometimes you'll see it and sometimes you won't, if I've remembered to hide it. But we try to start with random non-overlapping initial conditions. We specify particle number, spatial dimension, size of the box, number of integration steps. This is the interaction potential, and then I want it to visualize the results. And this is something that should be taken out of the code because it's ugly. Yes, do you want? I'm not going to give you the notebook right now, unless you really want it. It's kind of a mess. The actual functions are hidden away, and they're just a total crap show. Yes, eventually, sure. Yes, that'll be better. It'll be better if you watch for now. And then if people actually want access to this code, I'm very happy to share it. And I can also sort of walk you through ways that you can use it without me having to totally go in and clean up like 3 years worth of messy programming. Okay, code runs in higher dimensions. It runs in 3 dimensions. That's nice. You can run it in any number of dimensions if you want to, but you won't be able to visualize it. This is the best we can do for visualizing in 3 dimensions. Okay, do they work? This is a really good question. So let's address this. Okay, this is just completely unnecessary, but this is run in 31 spatial dimensions just because nobody can tell me not to. We simulate 100 particles in a box. We plot the kinetic energy over time. Now we have access to this kinetic energy because if you remember in the initial sort of problem statement, we're just incrementing positions and velocities. So what this means is we have xi of t, vi of t for all t for the simulation. So kinetic energy is really easy to compute from that information. I apologize for the scrolling. There's going to be a fair amount of scrolling during this talk. So it's constant over time. That's good. Next thing you might want to ask is momentum conserved? Okay, so we might set up a situation like this where we have a linear configuration of spheres and we start one moving from the left. And if we expect momentum to be conserved, we expect this sort of like transfer of the velocity particle by particle. And that is indeed what we see. So that's all good. I should make a remark. The momentum is conserved when the particles collide with one another. It is not conserved when the particle collides with the wall. At that point, the component of the velocity that the particle hits the wall just picks up a negative sign, and that momentum is not imparted to the wall. The wall is imagined to be sort of infinitely massive or infinitely whatever. So momentum is not conserved in these simulations if you're using reflecting boundary conditions. But if you use periodic boundary conditions, then this particle should fly off the left and come out on the right. And indeed it does do that. And then total momentum will be conserved in this case. So something to think about if you do decide you want to use this. So that's good, momentum and energy conservation. So one question would be, how do errors propagate over time? So we've built a Newton's cradle here, or I guess a better way to say that would be, how do errors build up when you encounter increasingly complicated collision situations? So this is a pretty complicated collision situation. If you have a particle whacking into one side of this, we know how Newton's cradles work. The other one should just pop out the other end, but you can code in a variety of terrible ways and it just won't work. It appears to work. If you look closely, you can see that the particles are doing like a very tiny amount of spreading out, but broadly speaking, this does a pretty good job, and you can play around and make this chain of particles quite long, and it still is not misbehaving. So that's good, because there's no magic here. This is just, again, just implementing those equations of motion. So they're doing a pretty decent job capturing reality here as well. Okay, so I did a simulation in 31 dimensions earlier because nobody could tell me not to. So one question is something crazy happen when we start going into higher dimensions? So here we're looking at 10 dimensions. And one way to test this, and this is not a very high quality test, but it is some sort of test, is to just set a single particle in isolation and send it down each of the Cartesian axes. Just to see what happens. So here we're running periodic boundary conditions. So what we expect to happen is the particle and we're plotting position versus time as we send the particle down each of the axes. So this is 10 dimensions and 10 separate simulations. The particle moves nicely to positive positions, and then it teleports to negative positions and then moves linearly and repeats the process. So that's what we'd expect for periodic boundary conditions. And then if we sorry for that. If we do reflecting boundary conditions, this is also sort of the behavior that we expect. So the reason why I'm showing you all of these super boring tests is because we are going to be using the hard spheres to try to do genuine physics. So I want you to believe that they work. And then we can also play pool. This is a terrible game of pool. There's no pockets and there's no friction. Although maybe playing frictionless pool would actually be a lot of fun. So I don't know, but this is totally a novelty item. Okay, people have any thoughts?
Yeah, I had a confusion. So all of this is forward Euler under the hood, and like if yes, then why? Like I'm assuming that you just use some sort of ND solve under the hood, and in that case, that should probably be optimized, right?
So I'm actually not using ND solve under the hood. One of the things that I want to talk about at the end of this talk is making the integration algorithms way, way better, because the integration algorithms can, I said at the beginning, forward Euler is like in some sense the worst integration algorithm you could possibly use. And part of this discussion is that it's actually good enough, and a lot of professional scientists will use this if they're not working on something that is sufficiently sensitive that you need to have a good integration algorithm. Another part of it is this needs to be updated. there's a lot of things about these simulations that need to be better. So yeah, and not just the integration algorithm, but like these should be GPU accelerated and everything. Like if you watch the CPU of my computer when I'm running one of these simulations, it's just like one of the cores is like operating at like 2%, and that bothers me because sometimes they take quite a long time. So yeah, there's a lot of room for improvement on that. Does that address what you were trying to say, or is there?
Yeah, so I mean, my question was why use forward Euler under these? Because I'm assuming you're using forward Euler because that's what you mentioned at the top.
Mm-hmm.
And
Yeah. Mm-hmm. Go ahead. Sorry.
you are using forward Euler?
Yes. Yeah.
Okay.
So Xerxes and I actually made some attempt to choose a better integration algorithm, because in some sense there's like, if you choose your initial positions and velocities for the hard sphere system, there's like a correct solution. Like the Platonic ideal of a solution exists. And if you implement it on the computer, you should expect some errors at the level of numerical precision. Forward Euler has errors much larger than that. And I don't think that there's really any reason we can't get those errors down to numerical precision. We tried reinventing the wheel, and that was stupid. I tried to like come up with a way to invent an algorithm that would get us down to numerical precision. There's just no reason to do that. So I have active plans in the near future to go to the literature and just figure out the best way to do this. It looks like other people have their questions or their hands up. Richard and Sotiris, I don't know who was first. So let's see.
I'm not sure either. So I don't want to step in front of.
Go on, Richard. It's okay.
Okay, cool. Yeah, I think you already answered a little bit. I mean, you're saying it's sort of not necessary to go for maximal precision, and you can study the phenomenon anyway. But it seems that if you have linear velocity, you could always sort of, from a given state, know a sort of potential set of collisions, right?
Yes, right.
So you could apply something like the GJK, right? So like so the first step is broad phase, splitting things into potentially colliding, then GJK on the swept spheres or whatever, swept circles, capsule intersections. And then you're down to, for example, if all of your initial conditions are expressed in rationals, then you always have a full precision answer to the story, right?
Okay, so what I'm doing right now is I'm writing down your suggestions. I'm not sure this I don't really know anything about a number of the things that you just said, and it might take us too far afield to go into this now. But
like the basic idea is just, imagine sweeping out a volume from your shape. GJK can tell you the sort of the sort of minimum distance for it. Essentially, it's just like, given two spheres and their trajectory, you can tell the exact point at which they will collide, assuming linear velocity, because there's no sort of acceleration in the system. So that's the basic idea. And at any moment, given the velocities, we can partition all of the objects into sets of objects which will collide in the next, collision set, and sets of objects which won't collide, for example. And you can include the walls in that picture.
Yeah, right. Well,
you're always
all
time in sort of large jumps. Jump to the next collision, because each collision event is a discrete event. You can always just jump to the next collision.
Yes, no, and my understanding is that sort of this is much closer to, if you want to call it the state of the art. This is much better way of doing these things. Yeah, and people are talking about Runge-Kutta and everything. Yeah, no, I know. One of the issues is while we're tweaking this, Xerxes and I are actively working on physics as well. And when it derails you for a month because your supposedly improved integration algorithm is unstable for some unknown reason, that sucks. And that happened to us earlier this year. So forward Euler does have the benefit that it is at least stable. And this is definitely going to be fixed because we're claiming to be doing serious physics here. So, okay, Sotiris.
Yes, it's two good questions. The first one is that if it has been examined using this multi-body simulations to maybe solve parking problems? Do they offer?
Oh yeah. Okay. So
that's the first
here.
one, and great. So you'll talk about it later. Great. And the
Yeah.
second is there has been great progress, and as a matter of fact, some surprising results in using neural networks. Excuse me, to perform simulations, yielding results, amazingly accurate results at a fraction of the computational power. And as a matter of fact, the first such result I had seen about 1 or 2 years ago had to do with simulating the whole universe in a fraction of the typical simulator used to do this kind of stuff.
Yeah.
Have you tried playing with this approach?
Well, so I was for a while, and I'll talk about this in a little bit. I was studying with some applied mathematicians, and they were actively sort of working in the intersection between scientific computing and machine learning, and this is generally speaking quite a cool space. Because it feels like you can sort of do a little bit of magic and get these accelerations that you shouldn't, that are surprising that you can get. Sort of very simple versions of this is literally just like using a neural network as a time stepper in your integration thing, but there are much more sophisticated ways of doing this. Yeah, it's a super exciting space. I do have a little bit in here about sort of applying machine learning methods in the physics context, but maybe this will be some slightly new direction for people. I don't know. That's cool stuff. Okay, I've been given the permission not to respond to this Twitter thing, so I'm going to not respond to it. Okay, so that's hard spheres for the moment. We're definitely going to talk more about these, but this is the general setup, and you all have immediately found all the holes in it. Good, we'll fix them. So if you don't want to use a discontinuous potential that involves infinity, you can use Leonard-Jones, which sort of has this bizarre form, and perhaps I could have written this a little bit more clearly, but it sort of has a 1 over r to the 12th minus 1 over r to the 6th, and it looks like this. So this is like a continuous version of the hard sphere. So sigma is going to be the diameter of the sphere here. Excuse me, sorry. And then we have this epsilon parameter. So as we drag these around, okay, as we increase the diameter of the sphere, our potential sort of, the radius of this potential sort of goes outward, as we might expect. And we can also vary this and increase the depth of this well. So this is going to be sort of an attractive interaction. The more deep this well is, but so attractive at long distances and very repulsive at short distances. So differentiable version of the hard sphere potential, and people use this a lot in the literature. What is a sort of a liquid of particles evolving according to Leonard-Jones look like? Looks like this. It looks a lot like the hard spheres, but you'll notice we have these regions of overlap now. So right now the radius of the sphere corresponds to the minimum of this potential. Before it was like the edge of the hard sphere potential. Now it's the minimum of the potential. So there's no sort of violation of the laws of physics here. There's no infinite energies. This is totally fine. So relatively similar dynamics, and a lot of people use this. So that's Leonard-Jones. And then you can also do things like the inverse square law, and everybody has already picked up on the fact that Ford-Euler sucks. Now, it's basically impossible to do these sort of to do inverse square law type simulations with Ford-Euler. The step size becomes really important, and you can find yourself in situations where if your step size is too large, you're stepping into a region where you have much higher energy, and then the particle is just going to zoom off to infinity and pick up all this kinetic energy that it didn't have, or do some other crazy things that you don't want it to do. But this is just proof of concept. This is just like a repulsive inverse square sort of scattering type thing. And Mathematica actually has built-ins to do this. So this is n-body simulation. We can talk about this towards the end of the talk. It would be cool to get some of this stuff into the n-body simulation framework, although I have other sort of thoughts about getting this stuff into the Wolfram language, and I'll speak about that at the end. But you can get some really complex physics here, and you need one of these sort of adaptive time stepping algorithms, so something like that, something more sophisticated than what we're working with. But again, this is sort of proof of concept and sort of survey, lay of the land, what these types of particle simulations can do. We have this huge range of length scales over which they operate, and you can kind of do a pretty good job using some of them. And some people actually use these for research in ways that are sort of not problematic. If you have a research problem that is not that sensitive to the very precise details of the trajectories your little agents are taking. So people were talking about packing. So you can sort of simulate crystals here. The animations are going to go a little bit slow now that we have a lot of particles. That's not to be confused with the underlying simulations. The simulations are going to be capable of handling more particles than the animations. But this is periodic boundary conditions, just sort of something closer to a solid density of hard spheres. And you can see that they're sort of spontaneously forming regions that look approximately like classical crystals, like these. This sort of hexagonal lattice shows up, and then you have sort of a different sort of hexagonal lattice over here, and you have these domain boundaries that separate these things. And if you let this evolve for a long time, you can imagine those domain boundaries are going to move around, and thermally things are going to settle down a little bit and stuff. But the simulations are totally capable of doing sort of classical crystal type physics. This is a big one. I didn't want my computer to run too long on this, but this is 12,000 particles. And at high density. And this is a good time to say, you know, these simulations can do this. If you want them to be outputting sort of dynamic animations of your 12,000 particle simulations, that's not going to look so good. But if you want to run the physics underneath and then do some sort of computations on that physics, you'll be able to do that. So again, this code has shortcomings, but it's not terrible, and this can be quite computationally intensive. So so you can the point is that you can study sphere packing computationally, and so you can sort of look at both ordered and random packing arrangements. I haven't looked into this super deeply, but like it's good to know. I didn't do anything special. Like I can show you the code that ran this thing. Just give me random initial conditions, 12,000 particles, and run for not that many steps, then you get something like this. And if you were in some situation, obviously you wouldn't necessarily do it for this particular case, but if you were interested in what is the random close packing of spheres in 3 dimensions, it's not a terrible guess to just take the density of the spheres in this little volume right here. There are better ways to do that, and you can imagine sort of taking this code and extending it to different situations where maybe you're packing in higher dimensions or something like that. That should be able to handle that. So yeah, you can definitely think about ordered and random packings. Now, some of you, I don't know, you might all be super educated and don't need this digression, but if you're not convinced that packings are a serious question deserving of serious inquiry, Kepler postulated in 1611 these 2 sort of very common regular packings of spheres are the highest density packings in 3 dimensions. So this is stolen shamelessly from Wikipedia. Give me 1 second. So this is what they look like. This is one of these is described as sort of like the way that you pack oranges at the grocery store or something like that. I can't remember which one it is. Maybe it's both, whatever. These are very regular sort of packings of spheres. And it was hypothesized in 1611 that this was the case, and it was proved in 2017. So this is no joke. This is, even the regular versions of these packings are very difficult to study in precise detail. And this guy, Thomas Hales, is the mathematician who did it. And he said this, this is a constrained nonlinear optimization problem involving up to 150 variables with many local maxima that come uncomfortably close to the global maxima. Rigorous approaches to problems of this complexity are generally regarded as hopelessly difficult. That's from a book called The Pursuit of Perfect Packing, which I recommend. It's very short and very cool. And I got it from Stephen Wolfram's Wolfram Data Repository copy of his personal library or something. Sphere packings are super important to optimal codes in information theory and telecoms. Yeah, they come up everywhere. It's sort of bizarre. My advisor was explaining to me that like the nucleons in the nucleus exist very close to random close packing density. So they're sort of everywhere. Yeah, it's very cool. Store cannonballs. Yeah, well, that was the original motivation for this problem. Somebody came to a friend of Kepler because he needed to store his cannonballs properly. And the guy was a mathematician, and he brought it to Kepler, and that led to 400 years of people being confused about this, Random packing of convex polygons is a tough problem also with practical utility. Yeah, well, man, random packings are crazy. And we're going to talk about disordered packings here briefly. I know it seems like a lot of you know about this, so you might not be totally impressed with the depth of my treatment here. But another thing that people think about is sort of packings of ellipsoids, hard and soft ellipsoids, and that becomes quite difficult and also relevant for certain physicists who are working on this stuff. It's the universal problem of optimal space, physical or abstract. Yeah. Okay, so does anybody want to talk about ordered packings or whatever this is before we start talking about jamming? All right. So disordered packings, jamming generally. So this whole section is basically stealing extensively from this paper. This is a really good paper. It's a review article just all about sort of the physics of jamming, and it talks about foams and emulsions and granular systems and all that. It's really cool. It's one of these sort of physics problems that's both deep and exists at the scale of human experience, which is kind of fun. I particularly enjoy thinking about things like this. Okay, so jamming of granular materials. So you have disordered packing, you have a disordered arrangement of matter, and it suddenly becomes rigid under a changing control parameter like temperature, pressure, or density. So figure stolen from paper. Right, so some examples are like toothpaste, mayonnaise, shaving cream, or a pile of sand. If you look at this figure here, if we increase the volume fraction of sort of these deformable soft sphere-like objects here, at a certain point they're not touching, then there's a phase transition which occurs when, the average number of contacts between the particles transitions from being zero discontinuously to being non-zero. And then as you continue to increase the density, these things actually start to deform and push against one another. And interesting physics exists at this phase transition. Yeah, Voronoi. I'm positive that this is related, although I don't have anything intelligent to say about it. Everybody should read this article. It won't take you that long, and it's pretty cool. And maybe they say something that I don't remember. So theoretically, it's difficult to analyze these systems. So one of the ways you might get a handle on this is sort of like there's a heterogeneous sizes of these spheres and these particles, and they're deforming in response to forces. So one of the ways you might hope to get a handle on this is very sort of crude macroscopic ways. You just sort of apply sort of a force or a shear to the entire collection of units and try to see if you can compute some sort of elastic modulus, bulk modulus, shear modulus, something like that. And this is actually the way people study these things, but they're difficult to study theoretically because you don't have affine sort of translation of the force. I'm not going to do a good job describing this, but it's something like if you imagine applying a shear or force on the side of this big collection of these particles, that does not mean that the form of the shear or force is going to look like the external version at any given particle, especially at jamming. So you might apply a force. Can people see my mouse, by the way?
Yeah.
Yeah, okay. So if you imagine looking at this middle cell here and applying a force from the right-hand side to the entire collection of particles, that doesn't mean that this particle in the center is necessarily also going to be experiencing a force to the right. There's a breakdown of affine physics in sort of a dramatic way. And this is a great visualization of this. So what we're looking at here is we have sort of a two-dimensional plane of jammed particles. The top panel is something like this. The bottom panel is something at the phase transition point. And we imagine just taking one particle and exerting a force to the right. So just pushing it to the right. In this highly jammed phase over here, the influence of this force decays pretty quickly. And blue means sort of positive, so you're pushing to the right, so the force is increased over there, and red means negative, the force is decreased. But at the jamming transition, you get this long range and sort of omnidirectional, highly complex propagation of the force through these networks of particles. So there really is like different physics going on at the jamming transition, and it's quite cool. People don't typically study jamming with hard spheres. Sometimes people study jamming with hard spheres, but typically instead people will use soft spheres. So putting this into our particle simulation framework, this is our interparticle potential. Again, it's 0 if the particles are not overlapping, and if they are overlapping, there's some sort of restoring repulsive force that depends on the degree to which they overlap. So this is the sort of like the separation between the centers of the particles over the radius, and the closer they are to one another, the larger this potential is going to be. And you can see in this case, there's going to be, if you imagine that these are spherical particles that are sort of overlapping with one another, there's going to be a lot of deformation. That's going to be a higher energy situation. So that's going to keep them sort of constrained there. So that's the potential. This simulation should not be taken very seriously. If you want to study jamming, we can have a discussion about how you can make the code way better, but it might look something like this. So we have these overlaps here, and you should imagine these shaded regions are actually the spheres sort of deforming in response to these contact forces with their neighbors. I had to do a little bit of fudging to get this stable. Again, this is in part a consequence of the integration algorithms, but this is very, very roughly what will happen as a system sort of jams. They push up against one another and the energy sort of finds a minimum. Right, and there's the regions of overlap are elastically deforming the spheres. That's what these models are saying anyway. So I already talked about external compressions or shears. You can also use this. I thought this was kind of cool. So the jam system will exist at sort of a potential energy minimum. And one way that you can get a handle on the elastic properties of the entire collection, we have the position and velocity information of all of these particles, right? And in a jam state, you can sort of, if you want to put the system in a jam state in a more sophisticated way than this animation that I was just showing you, you can do some sort of potential energy sort of gradient descent type operation, find your way to a minimum, and then you can perturb the system away from that minimum, and it's going to oscillate in all sorts of ways. If you can diagonalize the sort of matrix of these various oscillations, that will give you information about the elastic properties, which is kind of cool. And they talk about this in this paper. I didn't go into it that deeply, but if I was going to study this, I would definitely want to reproduce that result. Let's see. I'm assuming Leonard-Jones potential can also be used to simulate jamming because technically it also simulates soft interfaces of the spheres. That's a good question. I think that Leonard-Jones is technically long range, so that might affect it, but I hear what you're saying, and that seems quite plausible. It may be that I don't know. Yeah, refer to the paper. I have all these papers linked at the bottom of the presentation, and you can take a look. That seems plausible to me. And even if people don't typically do that, you should do that. That sounds like an interesting problem. Okay, right. So I want to give you some examples of people actually thinking about jamming in the modern sort of scientific literature. But first, I'm going to show you 2 pictures I took in my kitchen, because no good scientific presentation is complete without pictures that you took in your kitchen. So these are some suds on the top of a pot that I was cleaning. And if you look closely, we have a nice wet foam here. The people who think about jam systems also spend some time thinking about foams. We have a nice sort of polydisperse population of spheres that are sort of randomly not really packed with one another. You can get actually foams jam, but my understanding is that it's the drier foams that jam, because they have more restoring force when you deform them. So this is definitely not going to be have a lot of restoring force. But anyway, nice application of this. And here's another picture. This is so silly. You're just going to have to indulge me. This is an orange peel, and I noticed out of sheer boredom when I was holding this orange peel up to the light that, again, you have sort of like this cellular network of little, like, I don't know if this is oil in the skin of the orange or whatever this is, but it looks a lot like a polydisperse sphere packing in there. Yeah, okay. So I'm just gonna have to get a saved version of this chat history because I'm not sure I'm gonna be able to keep up with everything that's going on here. Oh, interesting. That's kind of cool. I'm looking at this phase-space bubble thing. And there's a cool, my understanding is that there's like one book about foam physics written by like these two people who are the real physicists who study foams, and that's about it. And they're from Ireland, and I read it and I thought it was pretty cool. So I'll talk about it, or I'll leave the name of that book at the end of this presentation. Okay, so that's sort of stupid examples. I do have an actual example from the experimental sort of literature here. Let me pull this up. Are people bored out of their minds? Is this going too slowly? Because I can sort of move on to different stuff. It's up to you. Cool. Yeah, this video that I'm not going to move on before I show you this because this is really cool. So this, and I'm biased because this came out of my undergrad research group, but I didn't do any of this research. So can people see green and black blobs of stuff? Okay, so before I play this, scale bar 50 microns, what we're looking at here is we're looking at a super dense collection of swimming bacteria. And just to get the lay of the land, all of these little black tube-looking objects are individual cells. Green, so this is a video which was filmed under a fluorescence microscope. Probably wasn't a fluorescence microscope, it was probably a stereo microscope, whatever. Green means activity. So you're recording on the microscope, and that gives you a sort of sequence of frames. And if, so they ran some sort of image analysis on this, which says if one pixel changes from one frame to the next, just color it green. And if the pixel stays the same between frames, don't color it green. So green just means things are moving here. And that's going to be relevant because, well, take a look. So just some general observations. This is simultaneously super cool and super disgusting. I worked with bacteria for a while. I thought that they were totally repulsive, but they do some interesting things. So you have sort of like these regions over here, which are like really flowing and sort of like viscous, turbulent, almost fluid type situations. And then you have in the non-green regions, you have the cells all sort of smashed together. And the reason why I'm showing you this is that these bacteria are jammed. So the exact same physics that we're talking about with jamming of spheres, I'll just play this again, is taking place. These cells are jammed with one another. And if you sort of try to look closely at what's actually happening in the non-green regions, you can probably believe they're sort of like moving around, but they're just sort of crashing into their neighbors and they're not able to go very far. And sort of the regions that go from black to green are in some literal sense like melting. This is like a phase transition in this population of bacteria. So pretty cool, totally gross. You could also probably simulate something like this with a particle simulation, but I would not envy you. It's pretty difficult to figure out like how two cylinders which are not oriented in the same way in space are going to sort of have steric interactions with one another and jam. That's a difficult problem, but it's not undoable. I hope people found that cool. I thought that was cool. Okay, let's see. Did people can see it or they could not see that? I see somebody said can see it. I just want to make sure. Okay, great. All right, where's my presentation here? Okay, so that the point of that was that jamming is real, and so is sphere packing. Let's see, are people seeing the orange again? Yeah, okay, that was my evidence that sphere packing is relevant to life. There are all sorts of actual reasons why sphere packing is relevant to life, but that's right. Also, all of these sort of silly examples feature polydispersed spheres, which means spheres of different radii. So we can also do that with this code. Again, not perfectly physical. There are still some regions of sort of overlap, which shouldn't be allowed to happen. But this is what, very roughly speaking, what the evolution of a polydispersed hard sphere gas will look like. An interesting thing that I sort of came across while I was encountering this literature for the first time, if you want to make a really, really dense mixture of something, I came across this in like a scientific paper or something. I'd never thought about it before, but it makes a lot of sense. You start with some particles of a certain size. And if you can roughly figure out, so like, let's look at the biggest ones here. If you can roughly figure out what the average size of the space between those particles is going to be, and then choose another sort of like, I'm imagining like sand here or something like that. Choose a more fine particle that is roughly the size of the average space between the bigger particles, and then you can figure out the average spacing between those smaller particles and fill in even finer particles. This is a way of creating like a really, really dense mixture. So if you found yourself in a situation where you had to create like a really, really dense amorphous collection of like, I don't know, whatever it would be, this is sort of a way to make a really, really dense solids. So anyway, that's neither here nor there. I just thought that was cool. Okay, that's the end of packing. So I'm gonna move on. I also, oh my goodness, am I already an hour in here? Okay, I've gotta hurry up a little bit. Do people have any more remarks on this? Okay, self-propelled particles. I won't spend too long on this. Self-propelled particles, essentially everything that we've been looking at so far, the only accelerations are coming from either the interaction with the boundaries or reflecting boundary condition, or some other particle exerts a force on the particle and causes it to accelerate. But if you want to model, for example, biological systems, they can accelerate themselves. This is a self-propelled particle. We're going to use exactly the same situation. You would have seen things like this before. It doesn't have to be biological, by the way. The first example is random walks. Here are our equations of motion like we've had before, and the force is now just going to be some random kick in some direction. Then you get stochastic evolution like this. Everybody's seen this in their StatMech classes. Sort of how foundations of some primitive buildings are done. Dig a hole. Yeah. That's exactly what I'm talking about. Yeah, that's cool. I mean, if I'm responsible for building a building, that building is going to crash down, so I wouldn't ever step inside. But theoretically interesting, we'll say that. So these random walks here were done with this is a random orientation force, which it's a kick which randomly reorients the random walker with a uniform distribution in angle over the circle. So it's just going to choose a random angle between 0 and 2 pi, and it's going to take a step in that direction. You get walks that look like this, but you don't have to choose a uniform distribution. You can choose a von Mises distribution, which, if you're not familiar with this is basically a Gaussian over angles. So it's sort of tightly distributed around a certain angle, but there is fluctuations around this. And some random walks with a von Mises distribution might look like this, where the angle that they're distributed around is 0. So they're very roughly speaking moving in a straight line, but they sort of have these meandering trajectories. And people actually, this is sort of like a pretty decent model of how bacteria will swim around on a petri dish if you have them swim around on a petri dish. And that's one thing that my undergrad group did. So one sort of an interesting extension of this, they had these cells swim around on a petri dish, but they put a regular crystal grid of plastic pillars in the petri dish, and then just put the cells under a microscope and watched how they interacted with these pillars. So they had this sort of like scattering behavior, essentially, where the cell might hit a pillar over here and it might swim around and change its mind and go back some other way. But at a certain point, it would leave the pillar at some angle in some direction. And that gives you a probability distribution. So you fix an impact parameter where how the cell comes in and hits the pillar. And then there's probability distribution, both in terms of where it leaves along the perimeter of the pillar and what direction it faces when it leaves. So what we're looking at here is if we imagine our bacteria move in perfectly straight lines, this is to give you an idea of what this probability distribution looks like at 0 impact parameter. So it's a stochastic scattering process. You're going to send these cells in A lot of them are going to leave over here. Some of them are going to leave over here. It's primarily sort of a forward scattering process, but there is some back scatter. Don't take seriously what's happening inside the dashed line. This is just sort of interpolation or whatever. So this is one question that you might ask is like, okay, let's imagine our bacteria are engaging in some sort of scattering process. It's stochastic. If we measure the distribution, what happens if we put actual cells in a grid? Can we simulate sort of the long time scale transport properties of the system? So it would look something like this. And this is something that I spent a lot of time thinking about as an undergrad. So the free space motion is the persistent random walk, which I was showing you earlier with the von Mises distribution, but then there's also this stochastic scattering behavior as well. So you can ask questions about like, okay, like over really long time and length scales, is this system just diffusing? Is it exhibiting super diffusive behavior, or what exactly is going on? And these simulations agreed pretty closely with what the actual bacteria were doing. It's kind of neat. It didn't end up with a publication, but that's just because I graduated college, so I didn't have time to finish this, but it was pretty fun to work on. And an interesting sort of combination of these techniques. And also one of these examples of actual sort of like scientific research being done using basically forward Euler style integration, and that's totally sufficient for the task at hand. Yeah, okay, so that's bacterial scattering and random walks and things. Do people have any questions, comments about that? Okay, and then bird flocks. So if you haven't seen, you should go on YouTube and look up starling murmurations. These things are awesome. They're so cool. This is a still image. You can get like tens of thousands of birds that are sort of interacting in some big swooping massive blob that exhibits these really rich, interesting sort of dynamics in physics. And I was fascinated by this. And I took a class on statistical physics of living systems, and we yeah, they're really incredible. And in this class, one of the topics that we covered was how these bird flocks are studied. So there's a lot people doing a lot of different things about this, some of them at various levels of sophistication. Some of it is like you have to know quantum field theory to even know what their models are talking about. So I just skip those because I don't really know quantum field theory, and that's why I'm not talking to you about quantum field theory. But we've been talking about self-propelled particles, so we're gonna talk about self-propelled particles here. I see people are talking about Boyds. Yeah, I know this is another way of doing this. I'm not exact. I don't know the exact relationship between this model and Boyds, but they're not too dissimilar. Excuse me. So this is the framework that we've been doing before. As always, we're just incrementing our position and our velocity, and we just now have a very fancy force. And this is from a Bialek et al. Paper, which is entitled Statistical Mechanics of Natural Flocks of Birds. And that's given in the references. So this is what the force does, very briefly. So it has some overall magnitude, and then there's some function here, and this is the unit vector function. So you give me a vector, I return the unit vector that faces in that direction. So the idea is that this particular self-propelled particle simulation is going to keep the velocities constant. And then we have three contributions. The first, or I guess the third here, is a noise term. So there's going to be some noise in their trajectories. And then we have two sums here. So looking at the index briefly, NCI are going to be the NC. So NC is a number. It happens to be 7. So the 7 neighbors to bird I. And the first thing that you're going to do is you're just going to average your velocity with these neighbors. So the birds are averaging their velocities with their neighbors. And then there's another sort of force here. Again, over the sort of 7 nearest neighbors of the birds. And it takes a more complicated form, but it's basically hard sphere repulsion at short distances. If the birds crash into one another, that's a hard sphere repulsion. At long distances, there's sort of a unit magnitude attractive force. So they're very roughly all interested in staying together. And then this force here, at short distances is repulsive. It's not as repulsive as the hard sphere repulsion at very short distances, and at longer distances, it's attractive. So they're basically trying to keep one another at a fixed distance. So this is a little bit more complicated. well, we'll simulate it and then we'll talk about some of the interesting aspects of this particular force law. So here's a two-dimensional bird flock. Okay, maybe if you squint a little bit, those might look like birds to you. I'm not going to go into the way that they do the data analysis on these things. It's quite rigorous, actually. They model them as condensed matter systems, and like you can look at velocity correlations and things, and they have very nice properties. So if I was going to try to study this more seriously, I might do that. But you can sort of squint at this and convince yourself that this might look like flocks of birds. Like, for example, they have these clusters that sort of stick together over time. And part of the reason they do that is that these interactions are actually topological and not metric. And what that means is that the birds are interested in their 7. That 7 is an empirical value that experimentalists actually sort of measured from real flocks of birds. But they're just paying attention to the closest birds around them, and they're not actually interested in how close those birds are. So it's just sort of like stay close to your 7 closest friends wherever they are. Rather than the way that all of the other simulations that have interparticle potentials have worked so far is give me the precise distance to the other particles, and that will tell you the force. So this is topological and not metric, and it makes sense that might be possible because these birds have brains and they're actually, doing computations as opposed to sort of these inanimate sort of simple liquid particles that we've been thinking about before. So that's kind of cool, and it's truly a different type of system. Here's a 3D bird flock. Again, this is largely for aesthetic entertainment at this point, because we can't really assess these things, and it's also very difficult to visualize 3D evolution on a 2D screen. But if you sort of just look at sort of the static slices of this, you might be able to convince yourself that they're sort of clumping together in a somewhat realistic way. Yeah, movement of humans in large crowds. That would be another great exercise. Part of this is like, some of this is like almost recreational computing. Like you can take some of these things seriously, and you can also decide to not take them seriously, and then you can have a ton of fun because you can simulate things like that and come up with reasonably plausible simulations and then be content with that and then go about your day. Of course, there are ways, like people take these simulations in particular. If you look at these velocity correlations, they obey well-defined patterns, and you can compare the velocity correlations that you have in these simulations with experimental data, and you get good agreement, which is why I'm showing you this. So these things are serious science, but they're also nice to look at, and there's nothing wrong with both of those things being true at once. I'm going to take a drink here if anybody has any thoughts.
I always thought that this sort of stuff happened like as an emergent property. So I was wondering if we can program a cellular automaton also to do this sort of behavior.
I have no idea. I think that it is emergent, and it seems like you should be able to do something like that. My understanding is that this sort of topological nature of the interactions is one of the important features for getting bird flock particular behavior. So, I mean, it doesn't seem like it would be that difficult to construct some sort of simple program that would count its topological neighbors as opposed to its like neighbors on some sort of CA grid, and do something with that. But I don't know. I mean, that would be cool to see. Would be interesting to look at Maxwell-Boltzmann. Yeah, well, I have a whole section of this talk about Maxwell-Boltzmann, and I really should get to it. I'm sure Xerxes is concerned that I'm not going to talk about our thermo stuff. Cellular TomTom, steering behaviors. Okay, I don't know about any of this. Okay, yeah, that would be cool, and people should do it, and you should post it on Wolfram community, and people will give you thumbs up or whatever the whatever the metric of success is over there. Yeah, so I have 2 papers at the bottom of this document that are related to bird flocks as condensed matter. This Cavagna et al. A lot of the physicists doing this are out of Rome. this is a good article. It's entitled Bird Flux as Condensed Matter, and they describe the experimental setups. They're cool. You set up cameras at multiple orientations, and you can sort of reconstruct the three-dimensional point cloud of these birds' positions over time and stuff. And also they talk about all the fancy QFT models and also the self-propelled particle stuff. So that's really cool. And then the other article, the BioLec article, that's where I got this particular simulation from, which is also a good read for other reasons. Okay, that is the end of just throwing a million particle simulations at you guys and saying, look at all these cool particle simulations. So I guess a more sincere way of ending this section is like, this is a highly general technique. And depending on how carefully you go about it, you can get quite a long way and do some serious science. And you can also just generally get sort of a conceptual understanding if you're not interested in going to your whatever fourth order integration methods and the like. So that's the end of the particle simulation section, although the rest of the talk is founded on particle simulations. It's just not going to be the primary focus anymore. So yeah, I mean, people can just chime in at any time. So the next topic is system identification. Yeah, traffic jams are cool. I see the traffic jams comment. I've thought about those for like 10 minutes one time, and I thought it was awesome. Okay, so this is the general problem here is seeing if you can learn physics, if you can infer physics from data measured from a physical system. I've spent some time studying this in graduate school, so I felt compelled to include it in this talk. And I also think it's cool. And the real reason why I'm including this, or that's not true. There are several reasons why I'm including this. One of them is that there is an easy and highly fruitful research topic that will come out of this, which is basically implementing all of this code in the Wolfram language. This is low-hanging fruit and worth doing, and a lot of people will thank you if this code gets put in the Wolfram language. So somebody pay attention if you're interested in this type of thing. Okay, so the general, we're going to be talking about something called Cindy. Has anybody heard of this, by the way? Just curious. Okay, that's all right. It's a sort of a fancy machine learning type thing that's making the rounds. The general idea is you can sort of teach a computer to do physics or a number of things, teach a computer to discover a model given data measured from a system. And this is this big question here. This is the field of system identification. Given data from some dynamical system, can you infer the governing equations? The algorithm that we're going to be talking about is the sparse identification of nonlinear dynamics. Nathan Kutz and people at the University of Washington, where I am, think about these questions. So I'm going to try to sort of, yeah. So Steve is a collaborator of Nathan's as well, and I worked with them for a little while. This work is pretty cool. I hope people find this interesting. I'm going to try to get into the statistics and get out as soon as possible and just start doing examples of this, because motivating it in the abstract is not as easy as just showing you that it works. Okay, we have some time series data x of t, and right now I'm going to treat it as a single variable function, but you don't have to do that. This works perfectly well with vectors, but we have limited time, and I was writing this at 1 in the morning. So single variable is, so say we have some physical quantity that's evolving over time, or a stock price, or a disease metric, or something like that, and we want to find a model. And this is basically the idea. We're going to compute x prime of t numerically. We have x of t, so we're going to numerically compute this derivative. And then we're going to try to come up with a bunch of things that f might be. So a bunch of candidate functions. And then we're going to try to find a linear combination. Those are called the library functions, by the way. So we're going to come up with a bunch of things that f might be. That's the library of functions. And then we're going to try to find a linear combination of library functions, which reproduces our data, with the further requirement that it be sparse. So you don't just want to take all of your candidate functions and just have them each contribute like a tiny little bit and then reproduce your data. Ideally, you want some sort of interpretable model at the end of this. So if you can pick your library functions well, then it might just be that a small number of them contribute disproportionately to the solution here. So this is pretty standard regression, but it takes a couple of steps to set it up. So let's take a look at some matrix equation, AY equals B. we can always represent a matrix A as just its column vectors here, and Y is just going to be some list of numbers here. If we do the matrix vector product, we're going to get this expression here. So this is going to be a linear combination of the columns of A. And we don't know Y. The idea is that we do know B and we do know A, and we don't know Y, and we're going to choose Y in a clever way to sort of accomplish this task. So B is going to be our X prime of T, and now this is going to be a vector because it's going to be X prime evaluated at all of our time points that we're considering here. So again, this is time series data. We have X of T at T1 to Tn, and we're going to compute X prime of T at T1 to Tn. And then we also have the columns of the matrix A, our library matrix, which are going to be library function I evaluated at all of the time points as well. And so that's how, in that way, if we're able to compute these things, we have a list of numbers, which is B, and then a matrix of numbers, which is A. And then we want to do we're basically going to do a regression to solve for Y. And with the further restriction that it be sparse. And the way you can do that is with the regularizer. It's not that important, the technical details of this, but if it's sparse, that means that your result will be interpretable. So I knew that that section was not very well written, and I'm going to leave it now and just show you how this works, because it is actually a cool technique, and it does operate, it works in practice. So I think an example is a much better way to show you this. Okay, so we're going to generate some fake data. In the real world, you have real data, but in my talk, you have fake data. This is some differential equation, first order system, really simple. You can make these any order that you want. You just have to be a little bit more clever, and I was not. So this is some differential equation. It's not particularly complicated. So we solve it and evaluate it on some grid. And then we're going to, excuse me. And then we're going to numerically compute its derivative. So there's a bit too much code on the screen here. But what this is doing is this is taking the finite differences, x of t2 minus x of t1, x of t3 minus x of t2, and then dividing by dt. So this is a very crude way of numerically computing a derivative, but it is nonetheless effective. So this is the solution to our equation. I chose this because it's like sort of squiggly and not exactly simple looking. So maybe the regression will have a hard time reproducing this sort of curve. So X is our curve, blue, or X is our solution to the differential equation. This is our data set. Blue is the numerically computed derivative. And then we have to compute a library here. So sol is, this is meant to be X. I didn't name these variables very well. But the idea, like I said, was that you come up with a bunch of potential functions that you think F might be, and then you evaluate them at all of your time points. So T's are the time point of our simulation. So this is the one function, which takes the value of 1 at every time point, which allows for constants to be included in your F. Then we have x of t, x squared of t, x cubed of t, sine of x of t, cosine x of t, sine of t, t cosine t squared, all of these things. You come up with a nice list of examples. You probably don't want to make it 1,000 candidate functions long because your regression is going to have a harder time converging. But we can numerically compute these things. So now the library is a matrix. And if you don't believe me, I can show you that. We'll just write these things as strings for a nice printing bit at the end. And then we just use this function fit here. So I'm gonna comment this bit out and show you what happens if we just take, so this is our numerically computed derivative. This is x prime of t. And if we just fit the library, we'll see what happens. Okay, so this is a big mess. But what it did was it found a non-zero coefficient for every single one of the terms of our library because it basically just did a least squares regression. And the thing about least squares is there's no penalty for making non-zero coefficients for all the terms, even if some of them contribute less than others. So like this is 10 to the minus 8 on this term. So there might be some reasonable sense in which we can suspect that that term is 0, but like, what about 0.04 here? Like, is 0.04 0? It's not clear that we've really learned any information. We might be able to reproduce the data with this fit, because we could, for example, integrate x prime of t over time, maybe applying this to a new range of data points, and we might be able to capture the data, but it's not clear that we've learned anything. So what you can do is you can use what's called regularization, and regularization allows you to impose additional pressure on your solution to behave in a certain way. What lasso does is it penalizes the one norm of the coefficient vector y, and it would probably take us too far afield to think about what that really does, but basically, or why it accomplishes the goal that it accomplishes. But the goal that it accomplishes is it tries to push your solution vector to be sparse, which is what we were talking about. Because again, we want our computer to spit out minus x of t plus 1 over square root of 2 sine t. And if we run the regression with this regularization, this comes out. And it's cool. You can see the flaws. You can see the imperfection of the computer, because it's doing its best to capture this coefficient, and it gets 0.999 instead of 1. And for those of you who don't know, such as myself, what 1 over root 2 looks like, this is pretty good. So the computer is learning physics. It's pretty crude, but the crudeness is largely my own fault. This technique is actually really powerful. So you can have it operate on chaotic systems, and it still works. Chaotic systems and multiple variables, PDEs, which I'm going to talk about in a second here, it really works. And the reason that it works is it sort of doesn't need to predict the chaos. As long as you can compute like the value of, for example, cosine of x of t on your computer, it can just see how well cosine x of t fits your data. And then this additional sparsity requirement gives you sort of interpretable solutions. So I think that that's pretty cool. I see there's a lot of stuff in the chat here. Does anybody have any comments while I read this? Yeah, right. So yeah. So you're promoting interpretability on purpose because you want interpretable models. So that's part of it. I read about AI Feynman a long time ago. I don't remember it, and I don't necessarily want to click on it right now and remember what it's all about. But a lot of people are thinking about these types of things, and part of the reason they're thinking about it, like this regression. First of all, this is not computationally intensive. You do not need a GPU. That computed in real time in front of your eyes, you know. And it's not exactly like, let's see. Okay, it's not that big of a matrix, but still, like you can do these regressions relatively quickly, and you can do them on matrices that have like tens of millions of elements on your laptop, on the order of minutes, you know. So this is efficient and interpretable and powerful, so long as you can construct your library, and that requires thinking. But you know, it works. Richard, what's up?
So it's doing like if I understand, like a linear least squares on the. So maybe I need to go over it again.
Right. So I can explain a little bit what's going on here. And it would probably be helpful if I typed it out, but I'm concerned it will go too slowly. So what it's doing is it's trying to minimize the least squares objective plus something else. And
plus the regularizer, yeah.
Yeah, that's right.
Yeah.
And the regularizer sort of it adjusts the least squares analysis to accomplish the goals of the regularizer. Another way that the Brunton Kutz group actually does this in their paper, they don't recommend lasso. I'm using lasso because it's built in. They do something called sequential thresholding least squares, which is you do least squares, you truncate the small coefficients, and you do least squares again on those truncated set of coefficients, and then you truncate the small coefficients again, and you sort of iterate on this procedure, and in that way you approach sparsity without having to use sort of the fancy regularizer stuff.
Sorry,
okay.
and the other question was related to, so on your sort of synthetic data set, and you're you're fitting like multiple time steps, right? So because you showed that matrix, the dimensions of the matrix had something by 15 or so, or
Yeah,
I
right,
just
right.
that right.
The 15, I think, is the number of terms here.
Okay,
I'm going to embarrass myself if I try to count this in front of you guys. But I think
that's all right.
so. Let's see. So the 1500 will be the number of time steps, or the number of time points that we did this equation over, because it's range 0 to 15, the step size 0.01. And then there's 14 candidate functions, each of which is evaluated at every one of those time points. And all of that is in this library matrix. So we can do sort of like a matrix plot, so you can see what this thing looks like. It's okay.
Nice, that's cool.
Big
so your
mess,
function putting the in sort of like spatial coordinates, not the higher order like velocity, acceleration, so forth. It's down at the base space, so to speak. Is that correct, or am I?
I'm not sure. I'm not sure I'm following.
So your functions are sort of predicting the sort of first order. Do you see what I mean? As in distance, not the higher order terms of the system.
So this is a first order ODE. And in some sense, this is
Right.
boring. I had to work really hard to get anything interesting to come out of this first order ODE. Maybe it will be more interesting if I start talking about some of the PDE stuff. I don't have any computed examples, but I can show you what types of questions you should think about if you want to go and look into this, because there are much more interesting questions than fitting this to an ODE. This is computational coarse graining section. You can take the same thing that we did with Cindy and apply it to PDEs. This is the same group of researchers at the University of Washington. They call this PDE find. It's a pretty straightforward extension. You're doing another regression. Now you have some U of X and T. So rather than just having a time series of a quantity, you have a time series of function over space. So this is going to be some, and it couldn't be a vector value function and all those things, but I'm just going to do one space, one time variable here. So we want to know the governing equation for U of X and T. And this is going to be our regression problem. So we want to solve du dt is equal to some library times some y. And we're going to decide and compute the library, and then we're going to use regression to find y. Now the library is going to contain derivative terms, though. So it's going to have things like du dx, second derivatives, u times du dx, things like this. So you're going to form combinations of derivatives. And here you get into like not exactly squirrely territory, but you have to think carefully about how you numerically differentiate your data. If you're confronted with noisy data, for example, and you do finite differences, that's a terrible solution. And your numerical derivatives are going to be bad, your library is going to be bad, and your fit is going to be bad. So this is something that has to sort of be thought about carefully, but it's not really that hard to do this in many situations. And then we'll just run the exact same sparse regression in Mathematica. I didn't have time to do this, so I don't have a fully computed example, but I'll walk you through what you would do. These are some 1D random walks. This is time on the horizontal axis. This is space on the vertical axis. They all start at the origin. They do some 1D random walk. Coarse grain this to get a surface. So here's our coarse graining. We use smooth histogram 3D. This is a cool function for getting turning something like this into a surface. And now this takes the form of U of X and T. So time is evolving this way. Is it clear what this surface is up to? This is the density of these random walks, and time sort of extends in this direction, and space is transverse to that. So this is our U of X and T. This is a surface. We can numerically differentiate the surface, both in the time direction to give us the left-hand side of our PDE find problem, and in the spatial directions, and maybe you can take further time derivatives and things to get the other terms of the library. And then you just repeat the sparse regression procedure. And I've confirmed this in in Python. I didn't have time to map this over into Mathematica. You will find the diffusion equation if you do this, as you would expect. So first of all, I'm going to now talk about cool problems that I think people will find interesting. But are there any questions on the basic procedure of PDE find before I do that?
I had a question. It's not on PD, fine. It's on the previous section. If you want to take it right now.
Yeah, sure.
Yeah, so I was wondering if the dynamical system that we're studying, if the equations of motion um, have an inherent noise, like the bird flocks that we were studying, the equations of motion themselves had a noise component. Is there a clean way that these people are identifying the intrinsic noise in the evolution equations
Oh,
versus
I
the
see.
noise in
I
the
see.
data?
I see. So you're asking if it's possible to learn a stochastic term, like a genuine stochastic term, as opposed to just sort of like experiment or sensor error or something like that. That's a good question. I don't know. I don't know the answer to that. I mean, the way that you learn anything in this framework is you sort of you just sort of put it in the library, you compute it and you put it in the library and see if it comes up. But obviously, like any given stochastic process is going to be different from another stochastic process. And you can sort of think about these things in a non-careful way, and then you can think about them in a very principled way. And I don't understand the principled way. So it looks like Richard may have something in the chat about this.
I guess you could call that a non-principled way, because yeah, it's learning a stochastic differential equation model with a neural net, but it relates to like a variational principle and so forth, where you have sort of probability distributions within your model. So you're learning, you're learning the sort of mean and variance or whatever of your distributions, and those can go into your library functions.
Yeah, so I mean, so this is, I should say, I forgot to say this in the beginning, this is like a brand new space. So these papers came out in 2016 and they already have over 2,000 citations, so a lot of people are paying attention to this and there's a huge proliferation of research. Somebody please put this in Mathematica. This is like an afternoon of coding. You can get it on the function repository. And this stuff is really, really useful. And they're also, it's directly computable. They're building these Python libraries to like automate the Cindy process and things. And this is just like textbook Mathematica's territory. So this seems like the type of thing that should just be totally swallowed into the Wolfram language and would be just a good project. And I have a section about projects at the end. I'm concerned I'm not going to get there though. So Tiras, what's going on?
Yes, Matt. It's about a comment I wrote earlier. As a matter of fact, here we're doing the regression with coefficients and find out the relevant laws. It sounds very similar to what symbolic regression systems like AI Feynman or now I'm forgetting the name. Some more recent results do. They use machine learning, of course, deep learning, in order to find out not the coefficients, but the law itself, the symbolic expression itself, that would best fit the data. So in essence, discover the law, rediscover the law of gravity, so to speak, from the data. So if you'd like to comment a little bit of this, I think it's very interesting in the relation between Cindy-like frameworks and Feynman-like frameworks.
Yeah, I think that my understanding of Cindy is that it's trying to basically turn a symbolic regression problem into a numerical regression problem, and then at the end go back to the symbols. Like basically they're trying to discover these laws, which are essentially symbolic laws, but the way that they're accomplishing that is by numerically implementing them. Yeah, I'm not familiar with a lot of the other symbolic regression stuff, but this is just generally a really cool space.
Yeah.
Okay. Guys, I do want to keep moving here. I know that I'm delaying us, but there's all this Wolfram physics stuff that that Xerxes and I have done, and I did promise that I would tell you about it. Oh no, I have to tell you about this project first before we do this. Okay, we might not make it to the end. I'm sorry. So coarse grained descriptions are not always easy to come by. So we can apply PD fine to a surface like this, we get the diffusion equation, but random walks are basically the easiest possible case, and that's why we chose it. So generally speaking, if you're not sort of in a very thermodynamic type limit, you might not be able to come up with a coarse grained description. So I have another show and tell video to play for you here. Where's my video? Here we go. Can people see a ridiculous wiggly object here? I'm concerned my computer is going to do something silly here. Okay, so here's what we're looking at. On the bottom of the screen, we have a 1D gas of hard spheres. And that's the simulation that's underlying this. And what we're doing here is we're just coarse graining with not a very large filter. And we're going to get some surface that evolves in time. And let's take a look at it and then we can talk about it. Okay. So the question that I'm interested in talking about before we talk about Wolfram physics is this PDE find framework, this Cindy framework. These things really work, and they allow you to computationally coarse grain. I have to find my presentation again. So they allow you to do coarse graining in sort of a principled way. If you construct your library in a good way, and you can do sort of a hyperparameter sweep to find the best hyperparameter for your regularization and all these things. But if you do your homework and that comes together well, then you sort of have the best possible coarse grain description. Whatever PDE find spits out is, it may not be the best possible. It's a very, very good coarse grain description given the library that you fed to the system. And this is an interesting opportunity because, like that surface that we were just looking at, that's a crazy surface. And it's a crazy surface because we're looking at like tens of particles and we're coarse graining over the scales of like small number of particles. So it's going to be crazy. And you can argue that that's not a good idea to do, and I might agree with you. But there's a more general point here, which is you can get really good, you can basically get the best possible coarse grain description if you construct your library carefully. And you get to choose how you're coarse graining. So the number of models in physics which allow for analytical coarse grain descriptions, I think, are sort of few and far between. And we've spent a lot of our time looking, oh boy, I didn't close all these menus, so there's too much information here. We spent this whole hour plus looking at all of these particle simulations of systems which are not at equilibrium, and some of them might be doing sort of weird things, having these weird interactions. All of these things, in some sense, can be coarse grained, and the coarse grain description can be found in this principled manner using this sort of these regression techniques. And you can do it as a function of like the resolution of your coarse graining procedure. So this is a really interesting idea. I think that it would lead to a good paper. I was hoping to write this paper myself, but I'm not going to be able to write this paper myself. Coarse graining as a function of resolution. So here's the setup. You imagine that you know the best resolution of your sensor. Let's say it's your microscope or your camera or whatever it is that you're doing. You know the best resolution. And you're considering physics on a scale that's much smaller than the resolution of your sensor, your microscope, whatever it is. Using this PDE find framework, you can coarse grain at the scale that you know is the maximum resolution of your sensor and make a prediction for what you will observe at that resolution. So I guess I'm not doing a perfect job explaining this, but it's something like resolution dependent coarse graining. And the idea is that maybe you have some microscopic model and you're not sure whether it conforms to reality. Maybe we could even do this with the Wolfram model. You have some sort of microscopic description, but you know you're only going to be able to examine it at scale blank, whatever that might be. This is a way to sort of systematically do this coarse graining. And I think that this would be a really interesting project, and I'm sorry that I'm not doing a great job describing it, but I do think it's a good idea. The other thing is that you can imagine exploring the behavior of the coarse grained descriptions as you vary the scale of your resolution. So, you know, at a certain level, if you zoom out far enough on a big enough system of hard spheres, there's just going to be a uniform density. And if you zoom in close enough, you're going to get some crazy undulating surface like the one that I showed you in that video. and there's presumably going to be some sort of continuous transition between these two regimes. And it might be interesting to sort of explore this. And there's nothing special about the hard spheres in this case. You can imagine doing this with any of the particle simulations, or if you want to construct your own, or you have experimental data probably wouldn't work. Simulations are a really good testing ground for this type of thing. So it does seem to me like there's an interesting collection of questions that can sort of now be addressed using this modern statistics type machinery that may not have been possible before. And the other thing to say before we finally move out of this section and start talking about Wolfram physics, is you don't have to coarse grain using just sort of density descriptions. Like this is a density description. And the crazy undulating hard sphere surface was also a density description. But you can do a lot of different things. And one sort of area that's a little bit exciting here is using machine learning to extract richer information as a coarse grain description. So you can imagine applying like a convolutional neural network to each frame of your simulation or something like that, and being able to extract sort of more rich information. And then passing that through some sort of PDE finding scheme. It's conceivable, like you don't want to be applying this super powerful machinery and just confidently declaring you've discovered something when you're just finding noise using really high powerful machinery to find noise. But it is conceivable that some dynamics are going to be hidden in the data, and that a good way to do this would be coarse graining using some sort of machine learning coarse graining. And then you can sort of imagine feeding it through one of these descriptions. Or maybe the coarse graining by itself will be valuable. So anyway, these are some things to think about. And the machine learning capabilities in the Wolfram language are getting better all the time. They're really easy to use. So maybe somebody smarter than me will be able to take one of these problems and take it in an interesting direction. Okay, I closed the chat by mistake. Visual interaction. Yeah, people are doing such crazy things now. The amount of sort of like learn blank from video using machine learning it just blows me away, and a lot of it is really high quality stuff. So again, I'm going to look through this chat in more detail later. Okay, if people don't have any more comments about this, and you're welcome to speak up now, I'm going to talk about some thermodynamics and Wolfram model stuff. Good. All right. This talk was supposed to be about hard spheres. I told you it was going to be. Sorry.
You saw the video.
I'm sorry.
You had an instruction. Don't let Matt not show the video.
Oh no, I did. That was the undulating surface was the video.
It's okay. It's just I'm working on two projects here, and I missed it. Okay.
No worries. It wasn't that important. It was just to give you an example of coarse grading and sort of scale dependent coarse grading, and why that might be an interesting thing to look at. Okay.
Recording. Thank you.
Yeah. Okay. So let's talk about Wolfram physics. This is totally different, by the way. This is still not fundamental physics. So my understanding is that most of the Wolfram model is actually supposed to be sort of an explicit description of the underlying constituent elements of spacetime. That's not what this is. We're going to be looking at hard spheres still. We're going to construct a causal graph from the hard sphere system, and we're going to see what we can make of that essentially. And Xerxes and I believe that this is actually a pretty cool thing to be thinking about. And it's sort of Wolfram physics inspired, and it has the potential to provide valuable feedback to the Wolfram physics project itself, while being in this actually relatively conservative domain of these sort of hard sphere simulations that we've been talking about. So we're basically going to be talking about temperature, although we want to do all of thermodynamics. We just haven't made enough progress to do all of it. Okay, so we've talked about a lot of stuff. In case you've forgotten what the hard spheres look like, this is what the hard spheres look like. Okay, so these are the simulations that we're going to be looking at. So I mentioned that we would talk about Maxwell-Boltzmann. In case people forget, Maxwell-Boltzmann basically comes from this. So in the canonical ensemble, if you hold the system at fixed temperature, the probability that it's in a state with energy E is the exponential of the negative of that energy. So a hard sphere with in n dimensions with this velocity has this energy. This is really standard stuff. Now, again, we're sort of ignoring the fact that it's a hard sphere. You can think about this as a point particle. We can talk about why this is not a completely senseless thing to do. But if it has this energy, which is just the kinetic energy, the probability distribution will be this. This is Maxwell-Boltzmann. And we can change the spherical coordinates to get the Maxwell-Boltzmann speed distribution, which basically for visualization purposes is what we've been looking at. It's easier to visualize, and we're going to get the same results anyway. So this is the speed distribution in n dimensions, and we can compute the normalization constant by just integrating that expression up there, and we can define our Maxwell-Boltzmann distribution here. Okay, so that was just like just a really quick overview of what this distribution is. The crucial thing about it is that it is a distribution that has one parameter. If we actually look at the distribution here, there's this parameter alpha, and 1 over alpha is kBt over m. So we're going to do a parameter fit, and once we know alpha, we basically know the temperature. So that's how we're going to go about doing this. And it's not the only way that you can go about doing this, but it is what we are going to do. Okay, so here's what we're going to do. We're going to take one of these simulations here. We're going to run it for a large number of steps. And the hypothesis is that this is going to equilibrate very quickly. And given that that is the case, we should be able to look at an individual particle's distribution of speeds over the course of the simulation. So this is not a time-dependent distribution. We're saying fix particle 1. What is every speed that particle 1 takes over the course of the simulation? We can make some sort of histogram of these things. And well, this is what one of these histograms looks like. And the hypothesis is that if these systems are equilibrating quickly and the hard sphere gas is behaving like the ideal gas, then you should be able to get a pretty good fit to the Maxwell-Boltzmann distribution. So this is what we're looking at here. So we have a 2D simulation, 15 particles. We run it for some large number of steps in a relatively small box. That's basically this just for 100,000 steps. Particle 1 takes all of these speeds over the course of the simulation, and they form some sort of distribution. We perform a parameter fit, which is what this blue curve is, and it's a single parameter, and that parameter is going to be m over kBt. So 1 over that parameter that we fit is proportional to the temperature. And we know kb, and we know m, so we know the temperature. And so we did this, and we get some number 0.21 for particle 1, and then we repeat the same procedure for particle 2. So particle 2 has all these speeds over the course of the simulation. We make a histogram, we do a parameter fit. It conforms reasonably well to the data, and we're seeing the same temperature here. So basically what we're doing, and we can look at all the particles, and they're going to show up the same. So basically what we're doing is we're turning each individual particle into a thermometer just by monitoring what it's up to over the course of the simulation. Again, there are other ways to measure the temperature, but this appears to be stable across the individual particles in any one simulation. So if this is indeed the temperature, we should be able to control it just by manipulating the initial conditions, because that's the only thing that we basically have the ability to control here. And the only options are initial positions and velocities. So basically, if we increase the average initial speed, which is what we do here, all of a sudden 0.2 is going up to 0.8. And if you look at the particles, it looks like their speed is tracking with this as well. So increasing the speed increases this measure of the temperature, which is what we'd hope, because temperature is, roughly speaking, the average kinetic energy of the particles. So if we increase that, we hope the temperature goes up as well. And if we increase the speed even more, the temperature is going up as well. So now this is 18. The absolute values or the magnitudes of these numbers are not that important. Excuse me, the relevant information is just that the temperature increases with the speed. So our thermodynamic description matches our sort of rough conceptual understanding of how temperature should behave. And if you change the initial positions or the initial directions while keeping the speed constant, the temperatures will stay constant. Does that make sense what we're up to here? Yeah, okay. So that's how we're measuring the temperature, given the microscopic information here. We also are going to want to do other thermodynamic things, but this is in a very early stage. You can imagine computing the pressure by sort of counting collisions with the wall and keeping track of the amount of momentum that is imparted to the wall. And the change in momentum over the change in time is going to be a force. So you can imagine computing some sort of average pressure like this, although we haven't explored this very fully. And there's a number of other thermodynamic things that we're interested in doing in the long run. We're just relatively early in this stage of research. So Xerxes and I are particularly interested in getting the partition function and the equation of state and expressing them on the causal graph, which we're about to talk about, I promise. And I'll get there before the end of the 2-hour mark. But there's all of these things, correlation functions, distribution functions, and phase transitions and things, which would be really cool to first just explore in the hard spheres, because people have already thought about these things, but then to explore in the causal graphs, which I will introduce right now. So finally, we're getting to the Wolfram model. So let's take a look at the simulation on the left here, because I'm going to use this to help define the causal graph, and hopefully it will be clear what's going on. So we already saw something like this earlier. Particles bounce back and forth as they move across the box. And the idea is we're going to use the collision information to construct a graph and track basically the causal information through the system. So this is the causal graph on the right here. And each node is labeled by a triple. The third element of the triple is probably the easiest to understand. This is just the time step at which the collision occurs. So each node is a collision, and the third data point is the time at which that collision occurred. And then the first two data points are the particles involved in the collision. So at time 41, particle 1 and particle 2 collide with one another. Time 81, 2 collides with 3. Time 121, 3 collides with 4, and so on. And you can sort of start to imagine how this simulation on the left is being reflected in this graph on the right here. And the way we construct the edges, this blinking is bothering me, is here we see particle 1 and particle 2 were involved in a collision. Here we see particle 2 and particle 3 were involved in a collision. So if one of the particles was involved in this collision and then immediately was involved in that collision and didn't do anything in between, we connect those nodes with a directed edge. So particle 2 is involved in both of these collisions, so we make a directed edge in this way. Particle 3 is involved in both of these collisions, we make a directed edge this way. Particle 1 collides with particle 2 here, particle 2 goes this way, but the next collision that particle 1 is involved with is when particle 2 comes back. So that's why there's this vertical edge down here. And this is the procedure that we construct the causal graph from. Does this make sense? Okay, so this is a very simple simulation, so we're going to have a nice orderly causal graph. But if you imagine running some sort of actual simulation, like this is just for a couple of steps, our causal graph is going to start to get complicated. This is 75 steps. So in the previous examples, to compute the temperatures, we were running the simulations for 100,000 steps. This is going to be a big graph. So we're not going to print that out. I think my computer would melt if I tried to. But this is generally the thing that we're up to. So we're going to produce these causal graphs and see if we can extract temperature information from the graphs here. Xerxes, how should we proceed here? I don't have that much more than 5 minutes of material left to present, but I think it's a little bit more than 5 minutes. And I know you said you had to go.
Yeah, so Hatem will of course keep the session running. You can run even as much as half an hour if you like. I just have to go because there's a strict thing I have to actually be at.
Yeah.
But
yeah.
If you think you want to do this in a, for example, I can, if necessary, I can organize another session where we can take on for a whole hour if necessary. But if you think you just want to continue after this, that's also fine. Up to you.
Yeah. I don't want to bore people. I'm almost at the end here, so maybe we can spill over just by a couple of minutes.
Perfect.
And if people are really interested, I'm totally happy to speak with you. But we're really close to the end here.
Yeah. So you can continue. I mean, the session will go on. You can go on half an hour. Hatem will just moderate the questions, and later on, but if there are more things, we can always have further discussion if necessary.
Yeah, and people should Slack me directly if they want to keep
Yeah.
talking about this.
Best is to
Okay.
put your things on Slack so it's on record.
Yeah. Okay. Okay. So we're almost done here, but I just want to tell you sort of the first actual sort of like sensible, genuine result that Xerxes and I are slowly sort of putting together and making more and more solid here. So what can we do? How can we perform a computation on this graph and extract some information which is equivalent to the temperature? So we can count collisions over time. Oh, thanks, Satiris, that's nice. So we can count collisions over time because each collision is a node here, right? And the third data point labeling these nodes is the time at which the collision occurred. So we have number of collisions which occur over time. And if we run a big simulation, we can plot this, we get a really nice relationship. So the number of nodes that are sort of being added to the causal graph as time goes on, and you should roughly think about this as time flowing down the page here. It's accumulating in some linear way. Maybe the slope will have the information that we need. So the first test that we did when we were investigating the temperature for the hard spheres, and we were doing it directly from Maxwell-Boltzmann, was, does increasing the speed increase the temperature? So run this test. This is not labeled in the most clear way, but velocity disk essentially means like average initial speed. So as we increase the average initial speed here, we see that these slopes, the number of collisions over time, which is to say the collision rate, is also increasing. Okay, so it's at least tracking the trends that we hope to see. So it's possible that the collision rate, which we're going to call R, contains information about the system's temperature. So let's test this rigorously. And I'm about to show you something which has too much information on it, but we'll just dwell on this until everybody understands what's going on. So this plot has a lot more information than this plot here. It has a lot more simulations that went into it. So on this axis, let me just say conceptually what's going on here. We ran each one of these lines. What's the best way to introduce this? We ran a number of simulations. Yes, the best way to do this is to talk about one line at a time. Okay, so fix your attention to one of these lines. So we'll fix the area of the box, we'll fix the number of particles, we'll fix the radius of the particles. So everything is exactly the same. And the only thing that we do is we change the average initial speed. So we'll increase the average initial speed. And we already saw that that's going to increase the temperature. That was what the histograms were showing us. And it also increases the collision rate, which is what this plot shows us. Increasing initial speed, increased collision rate, and the histograms, which I've closed, show increasing initial speed, increasing temperature. Now, what we do is we plot the temperature on one axis and the squared collision rate on the other axis. Now, this is confining our attention to one of these lines. And then the different lines are, let's vary some sort of, I guess you could call it like a hyperparameter or something. Let's vary in this case, let's vary the area of the box. So that's going to change sort of the average density of this box. And then we do the same thing. We start with some slow speeds, and then we increase the initial speeds. So each of these data points along these horizontal lines is a full simulation with like 100,000 time steps or something. Excuse me, I'm sorry about that. So the idea is there a linear relationship between temperature and squared collision rate? And this plot says yes, and it holds for a variety of sort of densities. And we actually know the precise value of the slope here. And you can vary the densities in a different way. So this is exactly the same plot. Temperature over here, squared collision rate over here. Confine your attention to one of these lines. We run a bunch of big simulations, and we get the relationship between KBT and R squared. And then we increase the average initial speeds and do it again. So these are linear trends for a range of densities. So just to be very clear about what this means, the temperature is in the causal graph. The collision rate is in the causal graph, definitely, because look, here are the number of nodes, they're labeled by the time. You can sort of imagine like foliating the causal graph, which would be like the graph theoretic way of describing this, but you can also just look at it. Like how many nodes occur by t equals 13? Well, 1, 2, 3, 3 nodes by t equals 13. How about 74? Well, it's however many nodes are up here. So you can count this directly from the causal graph. That gives you a curve like this, which is the number of collisions over time. You measure the slope, that's the collision rate, and the collision rate directly gives you the temperature. They're linearly related. So the temperature is in the causal graph. And that's pretty cool. Reminiscent of interaction vertices in the Feynman diagram. I believe you. I told you that I don't know QFT yet, so I'm not going to make any comments about QFT. So that's really cool. So we're seeing that the causal graph has some physics in it, right? And it's not that hidden. And the other thing that's exciting about this is we use almost none of the graphical connectivity of this causal graph to get this information. This is really crude way of prodding the causal graph and seeing what information it has in store. So just as a matter of curiosity, you might be interested where these numbers come from. So I'm happy to tell you how that's going. Relatively straightforward thermodynamic calculation if you want to compute the relationship between the temperature and the squared collision rate. So you can compute the collision frequency for a single particle. It goes something like this. I'm going to go over this quickly because you'll understand why at the end. This particle is going to sweep out some sort of rectangle in space in some unit of time dt. The density in the box, the density of particles in the box tells you how likely it is to encounter a particle as it sweeps out this area in dt. Because if it encounters a particle, then that's going to contribute to this collision rate here. So the number of particles it encounters is going to be the density of particles times the area, okay? And then the number of particles per unit time is the collision rate of that one particle. You can compute what this is. And okay, this is the result, whatever. Then you can get the total collision rate from the single particle collision rate doing this calculation. The details of this are not that important. You plug everything in and solve, and you get that KBT is equal to r squared times a squared over n to the 4th pi d squared. And this has some of the characteristics of what we want. I know that somebody just wanted to speak up, but just let me finish this one thought. I'm almost done. This is our vertical axis of our plot. R squared is the horizontal axis. So this should be the slope. The only problem is that this does not reproduce our data. So this is what thermodynamics predicts. We think that this is just a finite system size effect, but we're sort of dotting our I's and crossing our T's and exploring precisely what this slope is. And it turns out that it's all of these ingredients. They just have different sort of exponents than we expect. And it's probably a small system size issue. Was somebody going to say something? Okay, that's fine. I was just curious.
I had a question, but like before that, I was wondering, so is your slope consistently lower than this, what you're expecting, or consistently higher, or does it just like vary and just not the same?
So I don't have a good answer to your question, but I have a bad answer to your question, which is that we're going in and we're sort of like fixing everything except for one of these variables at a time. And we're just seeing like, rather than going like a squared, it goes like a to the 4th. And rather than going like n to the 4th, it goes something like n to the 5th or n to the 6th. Rather than going like d squared, it goes like d to the 6th. So the short answer is that I actually don't remember whether it's like systematically lower or higher, but the power law relationships are just different. And it could be that this is just not really that interesting, but we were sort of surprised. I thought it was going to be entirely determined by volume fraction, but it turns out that's not true. So anyway, we're just sort of doing our due diligence on this. It sort of doesn't matter that much. We're considering a restricted range of slopes, like we're deliberately restricting our attention to slopes that are between sort of 10 and 100. If you make the gas really dilute, you can get a slope that's like in the millions or something like that. So there's a lot of ways of, there's a lot more that can be explored here. I'm much more interested in this, and this is the punchline, right? Like temperatures in the causal graph, and we use almost none of the information in the causal graph to get that. So what else is in the causal graph? And this is the thing. So predicting the slope didn't work. I'll close that section, and I'll just make some closing remarks here. So causal graph is the most interesting thing that we're up to, in my opinion. This is arguably the only new stuff that we're doing. The rest is just the rest of this talk was just me explaining some of the adventure that I've been on as I'm making my way through my PhD. And Dr. Wolfram was the one who proposed this hard sphere project, and it turns out that it's been really interesting and led to all sorts of new stuff that I didn't know when I started doing this research. So that's really cool. So we want to know how thermodynamics is embedded in the causal graph. This is like the most important research question that we're actually after. So in the short term, that means deriving as much thermodynamics from the simulations as possible. This is using position and velocity data to construct thermodynamic quantities. And once we can do that, like I had that list of thermodynamic quantities, pressure, partition function, all these things. Once we can do that, then when we go to the graph, we've like mastered that physics. We can just beat the crap out of the causal graph and explore every sort of way that it might possibly be hiding this information that we're interested in. Because you guys might already be reading the things that I have in bold here, but this is a really cool hypothesis. All of thermodynamics is in the causal graph. Now, we don't know whether that's true, but temperature came out like immediately. It was easy, it took us 1.5 years, it was easy. So we think that everything is going to be there, and that's really cool. And the implication of this is that there's simply another coarse-grained description of the hard sphere gas. So typically, the way that you'll see this in your statistical mechanics class will be the coarse-grained description is that of an interacting gas. So you have its equation of state is described by the virial expansion. So it's like the ideal gas law plus some terms like n over v squared and n over v cubed and so on and so forth. And you can try to write down the partition function, and it's difficult to do exactly, but you can use the cluster expansion, and that's how you can sort of talk about the thermodynamic description of the interacting gas. This is just something else. This says like, well, if you zoom out in that way, you get the interacting gas. If you zoom out in this other way, you get a graphical structure. And if this hypothesis turns out to be true, and this is like the crux of our scientific explorations here, that will be the case. And for every instance where there is a thermodynamic quantity that you can calculate directly from the microscopic simulations using position and velocities, there will be a graph theoretic quantity that can be computed using things like vertex degree and maybe some of the supplemental information that we have on the nodes and connectivity computations and things like that. And I just have no idea what that's going to look like, but it seems plausible that this will turn out to at least be partially true, which is pretty cool. Yorick, how can I help you?
Yeah, I think that's really interesting. I wanted to briefly ask what you mean by all thermodynamic information. So what kind of measures fall below that? Temperature, pressure, speeds of average speeds, which are based on temperature, or what else?
So I can go back to this list. Oh, I didn't close all my menus, so there's too much on the screen here. Give me 1 second here. Yes, so other thermodynamic quantities. Here are some things to look at. Yorick, your microphone is pretty choppy, by the way, but just FYI. So here's Xerxes and I have sort of our short-term sights set on the partition function here. I think that the pressure will be there. The pressure is literally the next project that we're looking into. This temperature, the slope analysis of the temperature has been taking a very long time to get through, which is annoying. The pressure will be there. It seems quite plausible that that will be the case. Once you have the temperature and the pressure, we're going for the equation of state. But if you have the partition function, like in statistical mechanics, just differentiate the partition function in 10 different ways, and you have all these quantities that you might want to care about, So like, it would be really cool to get the partition function from this graph. And I suspect it will be there as well. And then correlation functions and distribution functions is something that I'm quite excited about. Velocity autocorrelation functions. For example, the 2D hard sphere gas has a velocity autocorrelation function that has like a fat tail, like a long tail. And I think that what that means is that
what Stephen told me is that you're going to observe some sort of persistent structures that exist in the causal graph for much longer than you would expect if everything was sort of immediately thermalizing. So some sort of like vortex-like solution or something like that. And I don't really know what that means, but that's quite exciting. And then phase transitions as well. That would be really cool.
And would you have a general kind of way to axiomatize or define what you mean by a general thermonic quantity? Is there, I don't know too much about statistical mechanics, is there a general way to do that? And you could make precise the claim that graph theoretic invariance or measures correspond to those.
So I'm using that term colloquially. I'm not using it as a technical term. So basically what I mean is you just go down the list of the things that you typically encounter in your stat mech and thermo classes, and one by one you learn how to measure those from microscopic Newtonian information, which is sort of harder than I thought it was going to be, but that's neither here nor there. And then once you have it pinned down very precisely, then you go to the graph and you find it there as well. And the plus side, so this is getting me really to the conclusion here. And we can also talk a little bit more generally about the Wolfram model. Hard spheres are old news. People have been studying these since the 50s, right? So that's 70 years or something like that. But this causal graph, nobody appears to have thought about this, which is sort of hooray for us, you know, like this is a great opportunity, because I really do think, even if it turns out that like you know, the entropy is not in the graph or something, one of these quantities, if it turns out that that's not expressed in the graph, some of them will be, and because we already know that the temperature is, and that's really cool, because we know, by we, I mean people smarter than myself, know the hard sphere system backwards, forwards, and sideways. People have made entire academic research careers studying the hard sphere system, you know, and that means that we have a Rosetta Stone here. There's two languages, right? And one of them is thoroughly elaborated, and there's an entirely new language. And if the hypothesis is that these two things are ultimately encoding the same information, then we just get to do relatively straightforward language translation and express all of these quantities on the graph. And that's really exciting. Just a general remark. Anytime you find a Rosetta Stone is really good news. So for example, if you're doing Newtonian physics and all of a sudden you discover that you can do Lagrangian physics, technically those things are equivalent to one another, but you can do so much more with the Lagrangian. You can solve different types of problems, right? And if we just sort of have a general way of like taking everything that we normally do in StatMech and putting it on this causal graph, it's conceivable that other doors will open that it's just not exactly clear what they will be. And they might not be in physics. You know, networks are everywhere, right? Like, this might help Facebook do something. I'm not interested in that at all, but it's conceivable that all of these big social networks will be able to benefit from this. I think generally speaking, the state of affairs with network science, and I saw people talking about network metrics in the chat here. Yeah, these things are sort of constructed. They're not constructed necessarily from first principles. They're sort of constructed because people want to characterize such and such an aspect of a network that they're working on. So they invent some sort of centrality measure or something like that. Well, we're going to be inventing new measures for these graphs, like new directly computable properties of the graphs that happen to correspond to things like the energy or whatever. And well, that seems pretty exciting, because, you know, we have this really solid physics to build on and develop our foundation, and then who knows where it's going to go. Like, you guys who are actually working on fundamental physics are operating much more on the frontier. So this is conservative stuff, you know, but maybe some graph theoretic measures that we develop in this conservative context will be, we can rely on them more in the fundamental physics context, if we've sort of done our very boring homework and validated that they're effective. York, I saw your hand went up first, and then
yeah. I don't know, can you understand me better now?
Yes, I think so.
I hope so. Yeah, I'm sorry otherwise. Have you Have you considered what happens if you remove the labels from the vertices in that graph? Because it would be even interesting if you can obtain all the info
Yeah.
you want to obtain purely topologically. And especially because it seems like you don't necessarily need time, especially if it's stochastic, because then one edge would correspond in the limit something like a uniform time interval, maybe, hopefully.
Yeah, so that's a really good question. So I was sort of, when we first started doing this analysis, I was bummed out that we were looking at information that was encoded in the labels of the vertices, because ultimately the holy grail of this would be not only is all of the thermodynamic information that we care about encoded in the causal graph, but it's encoded directly in graph theoretic properties, as opposed to some function defined over the vertices of the graph or the edge of the graph, for example. And the way that we've done the temperature is defined based on functions on the nodes, is one way that you can think about it, labels on the nodes. But I totally agree. And I think that that is really worth trying to do. And it'll be interesting to see what types of quantities are basically topologically encoded in the connectivity structure of the graph, as opposed to the types of things where you have to sort of like ask a little bit more like, but for example, one way that you could imagine getting the temperature without actually explicitly using these node levels is you can imagine assigning sort of an average overall scale to the causal graph. And that way you can just do foliations and you can count the nodes per foliation. And then once you have sort of like a scale of like, all right, one of these foliations is roughly like such and such number of nodes, then you could probably recover the temperature in some sort of large limit. And we've thought about that a little bit, but not in a high level of detail.
In that specific case, I think there would also be interesting information about the density encoded, because if you have foliation, it means the nodes on one layer of the foliation are called independent, so meaning collisions that basically occur independent of each other in or roughly at the same time. And if there are few of them, it means that the whole thing should be pretty sparse. But if there are, right, something like maybe possible.
Yeah, no, and that's another really good point. We think Xerxes seems to believe that and I'm not throwing him under the bus. I just haven't thought about it as carefully as he has. Xerxes seems to think that something like the pressure or the energy is going to be encoded like that. Like you fix a foliation that defines sort of like a time ordering-ish of the causal graph. And then within any given sort of like space, like whatever, within one of these foliations, something of the edge structure in there might encode the energy. I mean, I'm super excited to look into all these things. Scientific research just goes very slowly sometimes. So, you know, we just haven't gotten there. Kartik, how can I help you?
Yeah, so my start mic is a little rusty. I might just be blabbering right now, but I was at the scale which you're looking at all these like microscopic phenomena, there is obvious time reversal symmetry, and the causal graph. I don't know if it even makes sense to talk about the symmetric reduction of a directed graph, but I'm assuming that if you just reverse all the arrows, it still makes sense, because at least the simulations are time reversal symmetric. And that's why I was wondering, you had also listed entropy as one of the variables that you might be interested in looking at. And I was wondering if there is time reversal symmetry in both the simulations as well as the causal graphs. Have you like given it a thought how it might arise, or like, I mean,
Well,
the second thermodynamic?
Yeah, so the observation that you just made about just like taking the causal graph as it is and just reversing all the arrows and asking whether that corresponds to time reversal symmetry, that's a really good question. It kind of seems like it should, just because like people were talking about at the very beginning, like this is linear motion with reflections on the boundaries or not. Like if you use periodic boundary conditions, that goes away. So it seems like you should sort of just be able to turn the causal graph backwards in some sense, which is quite cool. With respect to the second law, I mean, I have one observation and I don't really know where it fits into all of this. So one thing that we looked at right at the very beginning was light cones And if any of you were unfortunate enough to go read the original blog post that I wrote after the 2020 summer school in anticipation of this talk, which is not very good, we did talk about those light cones in there. And what that means in the context of this graph is this. So like, let's focus on this node in particular here. Pick any one, but let's talk about this node. The light cone is to be understood as sort of like, if you move away from this node, all of the graph that sprouts out of this node is essentially the light cone. So after one step, we just have this node here, but after 2 steps, it looks like it goes this way and this way. After 3 steps, it goes this one and this one goes to this one. And so you see that it sort of like grows this, it's like a causal cone, but light cones are all about causality anyway. So it's like not unreasonable to think about this as a light cone. And those very quickly, if you imagine sort of tracking the extent to which the light cone covers the rest of the graph, the causal information basically touches the entire graph very, very quickly. So, you know, that might be some reflection of the fact that it, like some sort of sensitivity to initial conditions or something like that. It's just like, okay, if you have this causal information from one collision is very quickly going out and making itself aware to all of these other collisions quite quickly. And that might reflect some sort of like practical instantiation of the second law. It's just like you're gonna have a very hard time tracking this because you have to track all of the downstream causal consequences. But you know, the second law is a little bit deeper than that, I think. And if I just start talking about that, then you'll know I'm very out of my depth. So
yeah, I'm just thinking out loud here, but like I'm assuming that instead of looking at the second law in its thermodynamic formulation, I believe in the way the causal graph formalism works, there might be a wider scope and an easier entry, a sort of gentle on-ramp if you think about this whole problem in an information theoretic way in terms of Shannon entropy and stuff. But yeah, I mean, that might be something people might be interested in looking at.
Yeah, totally. Oh, and now that you mentioned things that people are interested in looking at, I have like a list of problems that I put together from this talk, which I will show you once I've spoken to everybody, because I think that it's actually a pretty good list. Yeah, right, exactly. So I one of the reversible cellular automata from NKS is the one where Stephen basically describes it as like being a reasonable, not exactly like a violation of the second law, because obviously there's a finite number of states for these things, but like it just sort of like it's orderly for a while and then it just like fragments into disorder, and then it's orderly for a while and it fragments into disorder again. Yeah, I don't know what to make of that. It's sort of totally bizarre. Should be a measure of reversibility. It's bijection. I think that you can reverse these. Like from a Newtonian perspective, you can the hard sphere system is time reversal symmetric, certainly. I don't know. I probably should stop talking about this because I don't really see how it's all going to play out. But these are really good questions, and if you guys have more detailed thoughts, like I want to know, because I'm really interested in figuring out the science behind these systems. Like I want to know if we actually have like a new description of the hard sphere gas. That's not like earth shattering, but it's cool, and I would like to know. And it could be more cool than we think it is. So anyway. York, you had another question?
Yeah, sorry. I had several ones and then I lowered my hand again because some you answered. But the final one would be maybe, before I need to go, have you considered the variance, the variance of the graphs you get depending on randomly chosen initial conditions, or in other words, the graph distribution that you get, I don't know, fixed number of steps you run it and then look at the graph theoretic heuristic distance measures between the graphs you get, because that could tell you something about how broad of a coordinating of the causal graph you have to do, right? So if they all look very different, would mean something like to actually obtain thermodynamical information from them, you would have to investigate some very general property of them. If you, for example, spawn two of those graphs with the same temperature and they look very different. But if they all look very similar, it could even reduce to something as simple as finding motifs or prolonged structures in the graph.
Huh. Yeah, that's an interesting question. I haven't thought about. We haven't really. That's sort of like a simple computational experiment that we just haven't run. I suspect that you made a comment about sort of persistent structures. We're definitely going to look for those because there's sort of physical reason to expect that those will be there. The velocity autocorrelation functions in 2 dimensions being one of them. But no, I think that it's a good idea to sort of look at those distributions. I haven't the faintest idea what they will look like. My intuition tells me that it's going to just be like total chaos, but I don't think that that's quite right, because even though these things are sort of highly interconnected, they're not random. They have sort of, you know, at least enough order in them to reproduce the temperature very precisely.
Yeah, exactly. They must have some structure. Maybe if you're willing to share the computational stuff you have, I don't know if yeah, I would be also interested in maybe just trying that and telling you.
Yeah, no, I totally am willing to do that. And it's not pretty, but if you just define all the functions and don't look at how they work, then almost all of the code that I use to generate this presentation is written in this notebook, basically right over the figures. So I'm very happy to share this with people. I'm glad that there's some interest. As you go to infinite degrees of freedom, you lose reversibility, and infinite systems with nonlinearities are also subject to both. I have no explanation. Yeah, so the question of infinite systems. I don't know if I really have Richard, your comments are outstripping my pay grade yet again. I'm sorry. I don't have anything intelligent to bounce back on this. Are people interested in seeing this project list that I've put together here? I tried to make it good.
That'd be nice. Maybe you could send it along with that notebook, Matt, on Slack.
Yeah.
And very nice. No, I was just gonna say, if people don't have any more questions, let's thank our speaker, Matt, for this very wonderful talk. And again, if people also have more questions, feel free to ask them on Slack, and Matt will get back to you.
Am I being kicked off this call?
No, it's fine. Do people have more questions? If so, please ask them now. If not, then we can just go back and work on our projects.
Well, you guys have been super patient, and I don't want to tax your attention more, but like this is a pretty good list. So everybody, I mean, it seems like a lot of people have already left. So if you're interested in leaving, by all means, please leave. But if I'm not being kicked off the call, I do want to read this just to talk about.
Please, go ahead.
Okay. So we had 3 sections of this talk: particle simulation, system identification, and hard spheres in the causal graph. And for whatever reason, I didn't categorize this with particle simulations, but I have a bunch of problems associated to each of these, and I'll just sort of go down the list here. I'm positive that there are scientific papers in here. Some of them might be quite good scientific papers, and some of them might be sort of like an afternoon of programming in the Wolfram language and then submitted to the function repository or something. So everybody told me within the first 5 minutes of the talk that my integration algorithms are not good enough. I agree with you. Let's make that better. More stable, higher accuracy, less wasteful. Excuse me, I'm sorry. These are all really good things to do. And hardware acceleration, sort of related to this, like these are not hardware accelerated at all. And you know, if you want to do large scale simulations of particle systems, and sometimes people do, like if you wanted to use a particle simulation to develop an accurate like molecular model of the way a gas actually is, so you know, you have some like nitrogen gas or something, and you want to use like a hard sphere model to make predictions that will be identical to the behavior of some volume of gas, that is apparently very hard to do. So we can use these to explore physical principles. And that's not to say that our conclusions are invalid by doing these simulations, but you need like trillions and trillions of time steps at super, super tiny spatial resolution in order to like sort of accurately capture gases as they are literally manifest in the universe that we live in. So I don't know if that's necessarily a good thing to focus on, but definitely GPU accelerating these codes, making them more stable, because that allows you to explore things like solids and interacting liquids, and you know, you can imagine doing sort of like a stellar dynamics type simulation where you simulate the formation of a galaxy or something like that. On my laptop, that would take like 1,000,000 years or a month. I don't really know, but I suspect it's closer to the latter. But if you GPU accelerate these things, they become much closer to sort of day to day. So that's a good problem. It would be fun. Make the periodic boundary conditions go faster. They're slower than the reflecting by a lot, and that's annoying. Put all of these particle simulations with good algorithms and good hardware acceleration into modular Wolfram language functions that people can use. I think that would be awesome. And I'm not, by the way, I'm not saying this like this is stuff that you should do. I'm saying like these would be really good problems if all of them were addressed, or if some of them were addressed. You know, if you imagine having like a built-in hard sphere function that, rather than using my crummy integration algorithm, uses like the best in the world. I don't know exactly what that is, and maybe it would be a good project for me to figure out what the best integration algorithm for hard spheres in the world is, and put that in there. But we looked at a whole bunch of things, like, I don't know, if the jamming algorithms are the best in the world, and you have like a jamming function in the Wolfram language, like that would be really cool. Take these simulations to new places. Plasmas are something that I didn't talk about. I would love to know more about. Particle and cell simulation is like a simulation technique, and I'm pretty sure that it's quite related to this. And then also, you know, the quantum mechanical versions of this problem, my understanding is that they're much harder, but it's conceivable that some of them could still be done. Solids and things like the POTS model. Richard, I see that you're posting here. GPUs get hot, yeah. Efficient GPU implementation of particle and cell. Yeah, exactly. So this type of thing, like, wouldn't it be tremendous if you just had like a plasma simulation function in the Wolfram language, and any, you know, high school kid who knew how to plug in the initial conditions could be simulating plasmas at the level of like a world-class scientific researcher. Like, that's exactly the type of thing the Wolfram language is good at. Is hierarchically building in sophisticated function that you don't necessarily need to understand in all the detail until you want to. This is just a perfect opportunity to make something like this happen. Yeah, and plasmas are tremendous from my understanding. System identification. Put SIND and PDE find in the Wolfram language. Somebody listening to this should do this. Last night, I finished putting together this talk at like 4 o'clock in the morning. It sucked. At like 2 o'clock in the morning, I figured out how to do that really basic crummy SIND example. What this means is that to do a high quality version of this and put this code in the Wolfram language is not going to be that hard. And like I said, these papers came out 6 years ago and they have thousands of citations. People are using this like crazy. So put it in the Wolfram language. It's not going to be that hard. You'll get a lot of props, and that'll be great. And it may even be possible to do something like automate your library generation. That's a harder problem because it requires a certain amount of knowledge about the problem at hand, but maybe you can figure something out. I don't know. So coarse graining the hard spheres as a function of kernel size, and using something like PDE find to explore the behavior of those coarse grain descriptions as a function of the size of your coarse graining kernel. And not necessarily just the hard spheres, like any of these microscopic simulations, you can do that for. It would be interesting to know if there's like a continuum or a hydrodynamic theory of like the flocks of birds that we were looking at. That sounds both hilarious and really interesting, like a bird flock fluid or something. I don't know. Presumably such a description exists, and it would be interesting to know what it looks like. Then I talked about this, which I think, again, I wanted to write this paper, and I don't think that I'm going to get to write this paper, but this is a really good problem, I think. It's like, how does the coarse grain description depend on the resolution at which it is observed? and sort of the downstream consequences of this, and this is something that we talked about a little bit, coarse graining on graphs. So we talked about coarse graining from basically phase space, like the position and velocity information, but presumably there's going to be some sort of coarse graining that can occur on the graphs themselves. Like, what is that going to look like? And in particular, this is in bold because, you know, we're at the Wolfram Winter School, presumably to think about fundamental physics. These hypergraph models are operating at such a tiny scale, if it turns out that this model corresponds to reality, that in all likelihood, you're going to need some sort of coarse grained description to make any sort of sense out of them. Maybe this is something that can be computed and automated, you know, and that seems like a really interesting problem to sort of think about. I know that Stephen has been talking a lot about experimental implications of the Wolfram model. This seems like one way to generate predictions. I don't know if it's the only way. Again, I don't really know a lot about these models, but I find it hard to imagine that you're not going to be doing some sort of coarse graining if you're trying to be generating predictions that can be measured in an experiment or in some sort of cosmological observation or something. So that seems like a really good exercise if you can think about how to do it. Just sort of run-of-the-mill hard sphere stuff. All hard sphere statistical mechanics that's known, look for it on the causal graph. This is my sort of mission. I'm sorry that I'm not keeping up with the chat, guys. I see that you're posting in here. Graph reduction rules will allow you to study simpler structures. Gotcha. Yeah, okay. Well, I mean, this is what we're going to have to do if we're going to be taking the physics on these graphs seriously. And then, you know, there's more sort of mundane stuff, like the melting transition in the hard sphere gas occurs at a well-defined density. Like, I haven't reproduced that. I don't really know what that means, but it would be really cool to see that just like unequivocal evidence of a phase transition in our hard sphere code to show that it's really capturing all of the various areas of parameter space that people know about these simulations. That's a really cool question. Jamming, make the jamming code work. There are much more sophisticated ways than what I did. And then demonstrate jamming phase transition. That's another problem, which is really cool. And I think that there's just like a lot of cool stuff in this space. Do this diagonalization of small oscillations. The Van Heck paper is great on this. Measure some of these bulk moduli, shear moduli, elastic moduli, material properties. Jamming in aspherical particles, frictional contact forces, particles in finite temperature. This is also in the same review article, and those problems sound like they get much more difficult. And that, you know, if that's something that you're interested in, I think that there's a lot of work to be done there. Flow close to jamming sounds cool. Simulating foams. This is another thing where it seems like we should just do this, you know, in the Wolfram language, because I know that there's like one research group that like does the foam simulations for planet Earth. And like that, I'm sure that's not exactly true, but my understanding, everybody points to this sort of surface of all their code is what they talk about. So that should just be put into the Wolfram language. And then the foams have all this nice behavior so that you can vary them as a function of fluid content, and they exhibit phase transitions and things. Causal graphs in other systems, and I promise I'm almost done. I'm sorry that I'm going so over time. I've enjoyed this conversation. It's been really fun. These things are going to be everywhere. The causal graph, the hard sphere system is basically the first place that we looked. And in some sense, its causal graph is screaming to be discovered. I mean, it took a long time, and it took Stephen to have the insight to ask this question, but I suspect that many classical, at least, many body physical systems are going to have causal graphs associated with them. So go out and find them. This is the treasure map that I was referring to in my silly sort of thing at the beginning, is it's like, we have the Rosetta Stone with this system, and there's a bunch of sort of incremental work to be done to find these thermodynamic expressions on the causal graph. What other physical systems are well understood from a sort of a traditional model perspective that can also be described in terms of graphs? You go out and find another Rosetta Stone and sort of repeat this process. So try to think about this. I'm sure they're out there. I suspect that they're everywhere. And then just as a final thing here, I sort of talked about this a little bit at the beginning of the problem list. Full library of easy to use modular Wolfram language functions with every major computational model that people use to do research in the physical sciences. This is a ridiculously audacious task. This is like a career level task. And I'm totally audacious to be proposing this, but the whole magic of the Wolfram language is that it continues to build abstraction upon abstraction and sophisticated functionality on top of sophisticated functionality. All of these things should be implemented into the language using the best possible integration algorithms, the best possible hardware acceleration, and the easiest use possible. So, you know, as a long-term goal, so that students and researchers can just say, like, I'm going to go to the Wolfram language plasma simulation function, and I would have to work for like a year to get a better results than the built-in function in the language. And it's not just, it's like every model that you can think of. So all of your stochastics and all of your, you know, your flocking and your whatever, your icing model, all of these things, these should just be done the best in Wolfram language. And we can do that. You know, the function repository is sort of like the pipeline for people who aren't explicitly employees to get things into the language. And I think that people should be generally heading in this direction, because the world does not need to know about scientific computing techniques to do scientific computing. Somebody needs to understand how these work, and then like every high school student who's learning physics in the country can run a hard sphere simulation without having to think about this. Like, that's a really sort of exciting prospect. Because a lot of people might learn that way. Okay, Jesus Christ. I promise I'm shutting up. Yeah, and I've heard about NetLogo as well. Yeah, so I think that this mission would be sort of a cool one to see if it's actualized. Okay, these are the papers at the bottom of the notebook, and I'm going to share this notebook with you. I should thank people, Xerxes, who's not here, and Christopher and Stephen for proposing the project. Zach is a postdoc I work with, and Nathan, who I spoke about briefly, because these people have been helpful in getting me to where I am now, especially these three here. So thank you so much, everybody. And I spoke for way too long. I'm really sorry for taxing your attention, but you've been really great in sticking with me this whole time, and this has been fun. I hope you enjoyed it.
Thank you, Matt. This was very wonderful, as I'm sure everyone has enjoyed it. Well, thanks everyone for joining. If you don't have any other questions, then let's thank our speaker, Matt. And yeah, see you at the next talk. Thanks,
See you,
everyone.
everybody. And I'll get that notebook into Slack for everybody to use.
Sounds good. Thank you.
Okay, take care. See ya.
Oh.